quantum gravity. And so without any more wasting of time, I give the floor to our first speaker. We are lucky to have David Brizuela from Bilbao talking about covariance in effective models of quantum black holes.
Okay, thank you for the presentation. Thank you also to the organizers for inviting me here to give this talk. Can you hear me? It's connected, right? Okay, so today we're speaking about covariance in effective models of quantum black holes. This is a work done in collaboration with Asier Alonso Bardaji and Raúl Vera. So let me begin by some motivation. As has been explained this morning in the plenary sessions, loop quantum gravity is formulated in terms of triads and connections. The issue is that the operator associated to the connection doesn't have a well-defined operator counterpart, and then one has to transform two holonomies, right? And this is what are quantized. These holonomies are essentially the imaginary exponential of the parallel transported connection through certain path. Now, on the other hand, effective theories, as we understand them in this context, are classically looking theories in the sense that they will give us some equations of motion in a phase space and also an associated metric. And these are supposed to encode the main quantum effects of loop quantum gravity, right? Therefore, the usual approach here is to perform what is called in the literature a polymerization, right? If one sees a connection component somewhere in your Hamiltonian, you just replace by some kind of trigonometric function, like that, with certain parameter lambda, which is related somehow to the length of the path that you're taking, or the area of this path is going around, so that this parameter going to zero recovers the classical variable. This kind of polymerization procedure has been very useful in cosmological models, in homogeneous cosmological models, and has led to the singularity resolution, the very well-known big bounds in loop quantum cosmology models. So now the objective of this work is to construct such an effective theory for spherical quantum black holes in this context of loop quantum gravity, right? Following something similar to polymerization procedure. But the idea here is that we will be very interested and we will be very focused on doing something that is covariant. Okay, so we'll modify the general relativity Hamiltonian, but the idea of covariance, this Hamiltonian should be modified in a covariant way, in the sense that gauge transformations of the phase space still corresponds to coordinates. Gauge transformations on the phase space actually still corresponds to coordinate transformation of spacetime, as happens in GR, right? So this is the key work here, and I'll define it afterwards more precisely. Once we have our model, then we will analyze the singularity resolution for black holes with charge and cosmological constant. Okay, so let me just briefly show you how this polymerization works in homogeneous models. Let us assume a isotropic cosmology, which can be described just by one degree of freedom. This degree of freedom is encoded in these conjugate variables, B and V, and it will be coupled to a scalar matter field, right, with its conjugate moment. Then the classical dynamics, very well known. You have the GR Hamiltonian constraint, you have the energy density, and this will be the Freeman equation, which tells you that the Hubble rate, which is this A, will be the scale factor of the universe. So A dot squared is proportional to the matter density, energy density. And this leads to the usual Big Bang singularity. Now, if one does the same exercise, but now instead of this B, which is some connection component, considers this sign of lambda B over lambda, and does the same computation, now the Freeman equation gets modified, and then we have that A dot squared now is proportional to this term. So we have the classical term times what is here inside round brackets, which can be vanishing. In fact, when rho is equal to rho max, this is 0, and this provides the bounds, right? So now the scale factor can go to 0. It has a minimum, A dot 0, at that point, right? And this solves the singularity. Okay, so the idea is to do something similar in a spherical symmetry. So let me just show you a spherical symmetry in these triad and connection variables. Here we need also two conjugate couples. Have vacuum, no matter here, just geometry. And I will call this EX and KX as usual in the literature, and E phi and K phi. These are now X dependent. X is our spatial coordinate, right? And exactly two conjugate couples. And the total Hamiltonian constraint, the total Hamiltonian of the system is a linear combination of constraints. Okay? And here we have the Hamiltonian constraints, which has this form in terms of this variable, and the diffeomorphism constraint, which only has one component. Because we are in a spherical symmetry, then the angular components of the diffeo constraint are trivially vanishing, right? So we are working just with two, in this reduced symmetry model, we are just working with these two constraints. These constraints obey the so-called hypersurface deformation algebra, right? They commute on shell, right? The Poisson brackets between the different constraints is just a linear combination of constraints. So if we impose equations of motion on shell, this will be 0 and all the right-hand sides. And the metric is given by this expression, okay? Here we have the lapse and the shift, which are the ones that appear here, these meaning functions of the Hamiltonian constraint and the diffeo constraint. Here I didn't mention, but then using this notation, this H will be the smear Hamiltonian constraint, and this regular D will be the smear calligraphic D with the corresponding smearing function. Then these two appear there in a natural way, and then here we have the spatial metric, which we can read from here. Okay, here appears the inverse, and here we will plug in whatever appears in this bracket between the two Hamiltonians. These are the expressions in terms of the triad components. Now, the idea is that we have done this polymerization previously in the homogeneous case. We can do the same here, right? We can just take some connection components and introduce a sign and see what happens. But the issue here is that if we are looking for covariance, this is not so straightforward, because if you start playing here around and start introducing different functions, you will see immediately that this constraint algebra will get anomalies. They will get terms on the right-hand side which are non-zero on shell, right? So this is something that we don't want. We want to keep this algebra closed without anomalies, right? And there are some ways that there are several ways that this can be done. This is well known in the literature for several years ago. One can somehow carefully polymerize the Hamiltonian in this sense. Now, this sign replaces the k phi that was here, but here, for example, once you consider the sign of 2 lambda k phi, not just the k phi, right? And this form of the deformed Hamiltonian, for example, closes algebra. It has an anomaly-free algebra with now a different structure function as it had general relativity. However, the problem here is that this capital F doesn't have the correct transformation properties to be interpreted as the inverse of the spatial metric. Okay, so this is an important problem of this approach. Another problem was that also it was difficult to couple matter to describe collapse models and these kind of things under this model. But the main issue we'll be dealing with here is this part, right? Okay, so what do I mean by correct transformation property and what do I mean by covariance? So in order to have a covariant theory, we will need two things. Okay, first we will need a closed hypersurface deformation algebra of this form. Okay, we will have then a phase space with a Hamiltonian of that form, and then this will be first-class constraints because they close algebra, and these are then the generators or gauge transformations, right? So this capital phi will be any function in the phase space, and its gauge transformation will be just given by the Poisson brackets with the Hamiltonian differentiation constraint with corresponding gauge parameters that we can choose, right? Now, on the other hand, on the space-time, we have coordinate transformations, and we know how the metric changes under coordinate transformation. If we do a coordinate transformation parameterized by this vector field, right, the metric will transform as the Lie derivative of the metric. So the idea of the covariance then is that both transformations must coincide when we want to interpret this Hamiltonian constraint as the deformation of the normal deformation to the space-like hypersurfaces, right? So whatever parameter we plug in here, it should describe the same vector which we are doing the coordinate transformation, but in this basis of normal tangential, this normal tangential basis of vectors, right? So this epsilon should be here in the normal transformation, the normal direction, and the different physical constraint we want to interpret it as the transformations in the tangential direction of the space-like surfaces, right? And they should go here. So this gives us a relation between the parameters doing the coordinate transformation and the gauge transformation. And the result in summary is that one can define this metric in a covariant way and define this to be the inverse of whatever function appears there, as long as the gauge transformations of 1 over f coincide with the Lie derivative of the spatial metric. Right? And the other requirement is that this function should be a scalar function. Here, the issue is that since we're in a symmetry-reduced model, this constraint algebra is not providing any information about the angular part. If we were doing this in the full theory, then we will see here the full inverse of the spatial metric. Here, this part, this sector, this angular sector is fixed, and the only thing we know is that this metric to be covariant, to change properly in the coordinate transformation, whatever is here should be a scalar. Okay. Good. So looking at the Hamiltonian constraint again, this is what I've shown you before. Again, we will do an ansatz of this form, which keeps the derivative structure the same. That is, this G Hamiltonian is quadratic on first order derivatives of the triads. It's quadratic on first order derivatives and linear in second order derivatives. So we'll include here the most general Hamiltonian, which obeys that, which is quadratic on first order derivatives and linear in second order derivatives. And we will leave here these A free functions, which in principle could be any function of our 4 coordinates, right? And now we'll do this process. We will require, first of all, anomaly freedom, that is this calligraphic H, form a closed algebra with the different constraint. Then we will require what I would call the space-time embeddability, what I've seen before, that gauge transformation of 1 over f coincide with the Lie derivative of the spatial metric. And the last requirement is just that the classical Hamiltonian is recovered in a continuous way. Okay. So if we do this, these are extremely long computations, but unsurprisingly, it leads to a pretty simple Hamiltonian. Okay, so we started with a Hamiltonian that had here, I think, 6 free functions of 4 variables. We are ending with this Hamiltonian, which has still free functions, but there are only 5 free functions of Ex, of 1 variable, which is the only one which is a scalar. Okay. This is the first thing, so the complexity is reduced a lot, requiring this. But the other surprising thing is that you see here we have sinusoidal functions. Okay, I started speaking about holonomies. I'm motivating this in terms of loop quantum gravity, but this in fact doesn't have to do anything. It's not related to loop quantum gravity. I'm just requiring a default Hamiltonian which obeys these 3 properties as I just told you. And surprisingly, we get these sinusoidal functions here, right? This is also, the name of the functions is quite suggestive in this sense. We have named A, omega, and phi. This is, as this was kind of a wave or an amplitude with a frequency and a phase, right? We have this G, which is a global factor, that you can multiply the Hamiltonian by any global factor as a function of the scalar, and the requirements I just mentioned are obeyed. And the last one is this V, which is a potential, kind of potential there, which appears here, and will let us introduce a cosmological constant and a charge there. Okay. Okay, the other issue is that vacuum GR correspond to these values of the functions, all these 3 going to 0, the amplitude going to 1, and the global factor taking this form. Okay, I'll have to skip. There are several properties one can analyze with these Hamiltonians, but now what we want to do is just analyze a particular case and really check what happens, what kind of a space-time is described, right? So for that, what we choose is like, what I would say, like the minimally deformed Hamiltonian, which we are keeping this omega, what I call the frequency, but setting it to a constant. This is now a constant, and the other three functions are taken to are chosen as their GR values, right? Here, the only one that's left to be fixed is the potential. That, as I said before, will be chosen to describe a cosmological constant and a charge. Now, one interesting issue of this Hamiltonian is that, in fact, can be constructed from the GR Hamiltonian by a canonical transformation and a linear combination of constraints. If I start with GR variables, this what I have explicitly written there, GR in them, and I do this canonical transformation, you see that the EX and KX couple do not change. And K phi, I introduce this, what I'm looking for, the polymerization, and then I change also E phi so that the new E phi and K phi are still canonical conjugate. If I do that, and I take this combination, multiply everything by cosine, do this combination constraint, this is equal to the above Hamiltonian. This, I'm explaining, has interesting issue, but the issue is that we're using this now to motivate the choice of the potential and the area of radius, which wasn't fixed. As I said, we don't have information about the radius because we are in this radius model. So we take these two as our choice because these are the value in GR. If we start in GR with this potential and this value of the area radius function, I can construct, and I go through this process, then I get this potential here. Okay, it's the same potential. The potential doesn't change through this process, in fact. Okay, so now the structure function of this theory has this form, is non-negative, and one can introduce this function and rewrite this in this form. Now we see immediately now that since this must be non-negative, this whatever is in the round brackets should be non-negative, and this gives me an inequality for R, right? So this in general would restrict the values R can take. In classical GR, R goes from 0 to infinity, but in this theory, it will restrict it to certain domains, right? Whatever obeys this. In particular, in vacuum, if I just put Q and lambda equal to 0, you see that this mass function is a constant of motion. Then this inequality is written in this way, right? And then if capital M is a positive constant, I immediately have a minimum value for R, right? And then this will give me the singularity resolution. This doesn't happen though for M negative. If M is negative, then this doesn't restrict. R will be from 0 to infinity, and I will have a singular spacetime. For non-vacuum cases, when Q or lambda are non-zero, this is much more complicated. This applies, not more complicated, but essentially it reduces to analyzing the roots of a fourth order polynomial. How much time do I have? 5. Wow. So I have prepared so many slides. Okay, let me show you just then the maximal analytic extension of this spacetime we have constructed in vacuum. It has this form. And as you see now, what appears here is this R0, which is replacing the classical singularity. Okay, this will be a maximal analytic extension of Schwarzschild. If you cut it from the blue line, now this blue line is just a minimal surface, a space-like surface, which can be traversed without any problem. If an observer crosses the horizon of the black hole, then it will cross this surface without any problem and go appear over there in a white hole horizon, right? So this R0 now what it's doing is just separating a trap from an anti-trap region. Good. So we find exactly what I say, a perfectly regular and physically complete spacetime if capital M is positive. Capital M is negative, then this naked singularity of negative mass Schwarzschild is not resolved, and this model doesn't help in that sense. Good. Let me show you just the Ricci scalar. This is the Ricci scalar with all the parameters, right? Mass, lambda, and Q. If you see, this Ricci scalar is 0 in GR. No, sorry, it's 4 lambda in GR when you have cosmological constant. But it has singularities when R is equal to 0. has singularity, but it also appears another singularity here, which goes with R. R infinity also, we have an infinite Ricci scalar. So now if we want to get singularity-free spacetime with charge and cosmological constant, what we will need is a minimum for the R and a maximum for the R, so that the singularity at infinity is not seen. So essentially what will happen, the schematical is this picture. Okay, we have, as I said, this inequality for R that we have to take care of and analyze. It changes a lot with the different values of MQ lambda, but at most this, the saturation of inequality will define 3 critical values. On the other hand, the horizon structure of the theory is the same. We have a Killing vector whose norm equal to 0 gives me this relation, and then I have the same horizon structure as in GR. So this is GR, lambda bar equal to 0, and at most I have 3 horizons, right, separating homogeneous and static regions. At most, I mean, this can degenerate, can have 3, 2, 1, whatever number, right? And this is what will happen in our case. At most, it will appear R, R0, and R infinity, and then the domain of R will be reduced. If something like this happens, then this spacetime will be singularity-free. If R0, capital R, do not appear, then the spacetime will see the singularity as R0, and if R infinity doesn't appear, it will see the singularity at infinity. How much time? 2. Okay. Good. So then, in brief, the singularity-free condition we find, I mean, we have analyzed this, and there is a family here. You have this paper to check everything, and we have classified all the singularity-free spacetime in terms of conditions for the parameters. But in brief, in a nutshell, the spacetime will be singularity-free if it has a non-negative mass parameter, a non-negative cosmological constant, and the charge has a certain bound, relatively small charge. Then with these conditions, we have constructed the conformal diagrams, right? But in general, the conformal diagrams will be the same as in as the classical ones. The only issue is that this R0 will replace the singularity at R equal to 0, and R infinity will replace the infinity that appears in the Ricci scalar. Then we will have also black hole type of solutions with horizons, we will have extrema solutions, and we will have cosmological type of solutions. Okay. Okay, and this is all the pictures you can see in the paper or later in the discussion session if you wish. And essentially this is my conclusions. So we have constructed the most general Hamiltonian constraint under the restriction of having the same derivative structure as GR, having anomaly-free algebra, and space-time embeddability, and containing the GR as a continuous limit. We have analyzed in detail this minimally deformed model, just taking one deforming function. We have seen that singularity resolution is not generic. It applies only in these cases, which on the other hand, and surprisingly, or I don't know if surprisingly, but interestingly, this happens for realistic black holes. A realistic black hole in our universe has a small positive cosmological constant. Black holes have positive mass and a small amount of charge. Right? Then the R equal to R0 replaces the classical singularity R0 in the pictures, if you wish. And then if the cosmological constant is different from 0, we have also a maximum value of the area radius function that replaces the infinity that appears in general relativity. And that was it. Thank you very much for your attention.
Yeah, thank you very much. I think we already have one question.
Thank you for a nice talk. So I have several questions, but I keep the rest of them for the discussion. From what I understand, you don't have the ADM mass term in the Hamiltonian constraint, because there are some models that have that in the Hamiltonian constraint, and like the Gambini-Pulin-Olmeda model. If you include that, can you comment if that changes your your form of Hamiltonian constraint in the sense that, especially the form of the sines and cosines that you have there in.
But you mean which term? ADM term?
Yes, the ADM mass term. So there's a ADM mass term that appears in the Hamiltonian constraint.
But you mean like the boundary term, or?
So it's, yes, but it appears in the Hamiltonian constraint itself. So it's like the m over square root of Ex.
I don't know. I don't really know.
Okay. But if you add anything in the Hamiltonian constraint in the sense that a term similar to that, which has one of those variables, then that will change anything in your sines and cosines. The question is that is the appearance of the sines and cosines, are they unique, or you're just putting them because they mimic the polymer form?
I mean, they're unique if you consider these ansatz. I mean, I just shown you the ansatz we have started from. So these are ansatz. I don't know if the term you're mentioning enters in this ansatz or not.
Yes. So I mean, in the sense that the sines and cosines you had in the next slide, I think.
Yes, but those appear. Those are not chosen.
Okay. So there's no other choice. You just appear.
There is no other choice. Exactly. I mean, that's the point. We have these ansatz, and then we require these three conditions.
Okay.
And
it's
that's
not because you want to mimic the polymer.
No. This appears. That was the surprising thing of this computation, right?
Thank you.
Is there one more quick question? Yeah. I'll try to pass this through.
Yeah. Thank you. So at the end, when you obtain your final Hamiltonian, you say that it's just the canonical transformation of the previous one plus an additional term. So could you hope to recover this Hamiltonian from the usual regularization of the Hamiltonian by considering loops and the specific mu bar speaking maybe and some specific polymer functions?
If I expect to recover this Hamiltonian from, you mean this?
The one just above.
The one above, yeah. This is coming from this linear combination. I mean, you can recover it if you do this. I don't know if. You mean if there is any motivation for doing this linear combination?
Yeah, from a loop quantum gravity.
From the full theory perspective?
Yeah.
I don't know. I wouldn't know. I think there is none. Okay. But.
Okay.
Thank you.
Okay, then let's thank all David again. And then we can proceed with the second speaker, which will be Stefan Gielen. And
can you hear me? Yeah, okay.
Yeah, we can. And soon I hope your slides will also appear.
Yes, we have some technical issues.
All right. I hope that's not coming off my talk time.
Yeah, the floor is yours.
Great. So yeah, let me start by thanking the organizers for putting together this really, really inspiring meeting. It's been really great to be here and learning new things. As you can tell, my voice is a bit damaged today, so apologies for that. I hope I can get through this talk okay. So my talk is not so much related to black holes, but has more to do with fundamental questions in quantum gravity, to do with unitarity, what we mean by that, and the consequences we can draw from unitarity, in particular regarding gravitational singularities. The talk will be to some extent related to also the talk that Lucia Menendez-Pidal gave already yesterday. So there will be some repetition, but I will take quite a different perspective here, so I hope it will still be interesting. So these are our papers. We'll mostly focus on this kind of broader perspective taken in this essay that we wrote for the Gravity Research Foundation. So what do we mean by unitarity? Of course, in standard quantum mechanics, this is one of our fundamental principles, which has to do with the probability interpretation of the theory. Our dynamics should be unitary, or the Hamiltonian operator should be self-adjoint. So we would certainly like unitarity to emerge somewhere from whatever our theory of quantum gravity is in the end. So then we have to ask, what do we mean by time evolution, right? So of course t, the coordinate, is just a label, so it doesn't make a lot of sense to use just the coordinate time, but we can advocate this viewpoint that also Bianca already introduced to us on Monday in the very first talk, which is this relational viewpoint, right? Which many of us think is kind of the only way of making meaningful statements about evolution. So the clock should really be a matter field, right? So the dynamics of a system should be described relative to, for example, a matter field, which plays the role of time in a certain sense. So then we can ask, if we have such a well-behaved, physically reasonable matter clock, should we require this kind of time evolution to be unitary? There's certainly a clash already here with the general covariance of classical relativity, right? Because, of course, there will be many such clocks in general. And in classical GR, I can always find clocks with unusual properties. And then unitarity with respect to those can lead to strange predictions. And I'll illustrate that in one example, which hopefully makes that clear. So some higher principle seems needed. For me, it's not clear what it is. And in particular, I would argue that by choosing the right clock and going through this, it seems we can always resolve singularities in a particular sense, again, that I will hopefully make clear. So here's the model, which again was already introduced yesterday, but let me review that. So this is our cosmological model here. You have your FRW metric. You've got the lapse function here. You've got your scale factor A, and this is just a flat metric. Here, of course, you still have the freedom to choose an arbitrary time coordinate, which here is called tau, and of course that corresponds to the choice of lapse function. So there's two matter fields in this model, which of course are designed to be possible clocks for you. One of them is this free massless scalar field that you are very used to from quantum cosmology in particular, and the other one is a perfect fluid, which is characterized by an energy density and by an equation of state parameter, okay, which is arbitrary. Now, by doing some proper clever canonical transformations, you can obtain this kind of simple form of the Hamiltonian, where you have kind of this canonical pair here, V and pi V. So V is a suitable power of the scale factor, so you can think of this as encoding the 3 metric. You've got your massless scalar field, and you have these two variables. So this is a canonical pair which characterizes the perfect fluid. And in particular, this lambda is a conserved momentum, which is the usual conserved quantity you would expect in cosmology for this perfect fluid. And I also rescaled the lapse and redefined this n tilde here to simplify matter. So a very simple Hamiltonian, 3 terms. First comes with a minus sign, of course, for the conformal mode. This is quadratic, this is linear. Okay? So now this is still generally covariant, but there is a particularly simple choice, which is n tilde equal to 1. So, yes?
Where does T appear in the Hamiltonian?
Right, so I will come to that on the next slide. Hopefully that's clearer. So this is just a canonical pair that comes. So in a sense, this is the variable that is canonically conjugate to this conserved momentum for the perfect fluid.
But it does not appear in
That's right. The Hamiltonian is independent of T. Yes, that's right. And likewise, phi doesn't appear in the Hamiltonian because it's just a free massless scalar field and does not have a potential. So the Hamiltonian only depends on pi phi, not on phi, and it only depends on lambda, and not on T, which means that trivially you have 2 conserved quantities, and which is why these phi and T variables would be particularly natural matter clocks, right? Because they're always monotonic. So in this gauge choice, T is essentially your time variable, right? So you can essentially identify T and tau. So that is, in a sense, a time coordinate that is adapted to this choice of perfect fluid, right? In which dynamics becomes particularly simple, and you can go through this for particular examples. So for -1, which is dark energy, this is a unimodular time coordinate. For 1/3, W equal 1/3, this is conformal time, and so on and so forth, okay? Other people might be familiar with dust models, in which case this is just proper time. So here, perhaps this is a more, so people don't necessarily like perfect fluids very much, right, because they're not really fundamental, but you can derive this in a way that is much more general from unimodular gravity. So you've got this NO Teitelbaum version of unimodular gravity. So in this action, the dynamical fields are your metric. Lambda and T are also treated as dynamical fields, so T mu is a vector density. And if I vary with respect to lambda and T, I get these 2 equations, right? So this basically fixes the metric determinant in terms of this T field, and this tells me that lambda is a constant. So in this sense, this is kind of equivalent to a unimodular type gravity. And this T mu also induces what you might call a preferred global notion of time. So you can compute the total 4 volume in a region of space-time which has 2 boundary hypersurfaces, and it will be completely determined by the integral of this t0 variable, which you might therefore treat as a notion of time. Right? This is a time that corresponds to the total 4 volume. So in a sense, this is valid much more generally, right? So this was a cosmological model, this is much more general. So I hope that's more convincing. The point is now to look at the classical solutions first. So these variables t and phi evolve monotonically. So they would be very good relational clocks in the usual viewpoint. So I'm starting with t here, and I'm writing the solution, the cosmological solutions as functions of t. And of course, here you see that these solutions have a contracting phase that ends in the Big Crunch and an expanding phase that comes out of the Big Bang, as you would expect, of course. And there are these 3 kind of qualitatively different cases, but clearly they all have these singularities. Okay? And that's, of course, just what you would expect. The message here is that this is, the form of the classical solutions is now written with respect to one relational clock. But if I change the clock, if I express them in terms of phi time, they look completely different. Right? So you can see here from this plot, phi of t, the scalar field, of course, it diverges at the singularities, as you would expect. Right? And if this lambda is positive, so for example, you have a positive cosmological constant or any other perfect fluid present, then as the universe expands, the scalar field will kind of slow down and asymptotically will only go to a constant, right? So this clock kind of becomes very, very, very slow if you see phi now as a clock, and it never goes past a certain constant value. And so now if you write these solutions in terms of phi, of course, they take a very, very different form, right? So here you can see the singularities are no longer visible. They've been pushed out to infinity, right? Because in terms of this scalar field clock, the singularities are at plus minus infinity. But here, the volume diverges suddenly, right? And this is again because of what I just said, which is that the scalar field actually slows down with the expansion of the universe. So the singularities are now invisible, but now we have this divergent volume. The explicit form of these solutions highly depends on the clock. Of course, that is not surprising at all from the perspective of classical relativity. But now, of course, when we impose unitarity for these theories, we get completely different answers. And this is already what Lucia focused on yesterday. So we're doing the standard kind of Wheeler-DeWitt quantization, and we do require unitarity, which means that whenever you have a singularity or you have such a divergence in the volume, you have to modify the classical trajectories, right? Because the classical solutions would terminate. If you impose unitarity, that requires a reflecting boundary condition, right? So the state, in a sense, wants to disappear here through the singularity, but because you require the state to be, the norm to be preserved, the state kind of gets reflected. And so all these expectation values here remain finite, right? So these are just expectation values. Of course, fluctuations are very large. This was already a question yesterday. Fluctuations in general are large, so here I'm just looking at the expectation values. So this is your standard kind of, if you wish, singularity resolution that you might be familiar with from other models in quantum cosmology. This behavior is much more unusual and certainly hasn't been discussed much in the literature, although there is previous work, of course, which is that sort of classically here the volume diverges, but sort of quantum mechanically these expectation values remain finite, because again you had to impose reflecting boundary conditions, which here at infinity. So this is, if you want, the far future of de Sitter space with a massless scalar field, where the volume, the through volume, of course, of de Sitter space goes to infinity asymptotically, but in terms of these expectation values would actually stay finite, have some upper bound, and then go down again. So in a sense, you would connect this future space like infinity of de Sitter space to kind of a new era, or eon, I guess, as Penrose would call it, in the next universe where you are now contracting. So this is really quite unusual behavior, certainly from the perspective of the usual intuition, which is that we expect funny things at singularities, but certainly not here. Right? So the point I want to make is that these arguments apply to many kinds of situations. So this is some text which kind of summarizes what I already said more or less. So the classical solutions depend very strongly on the type of clock that we use. And so in T time we saw these singularities, the Big Bang, Big Crunch singularities, and in phi time we saw this divergence in the volume. Classically, the solutions would terminate. Quantum mechanically, we don't allow for that if we say our theory has to be unitary. So therefore, the evolution must somehow extend beyond points and become kind of non-singular. And this was already discussed by Gautier and Desmarais in the 80s in a conjecture. Okay. Just to reflect a bit on the choice of quantization method, that's kind of the last technical point I have. So of course here I'm not giving any details, but what we're doing is we're writing down the Wheeler-DeWitt equation in the standard way, and then we're choosing an inner product which in some sense is motivated by the form of the Wheeler-DeWitt equation in the standard way, identifying a metric on mini superspace and this kind of stuff. But of course one might argue that these things all depend on these choices, okay? So one can take different viewpoints. So here's kind of this more formal viewpoint of group averaging and Dirac quantization, which is kind of very popular. So here you have a constraint operator. You say a physical state is basically obtained from an arbitrary state by acting with this delta of the constraint, which you also put in here to define your inner product. And usually then you also require this constraint operator to be self-adjoint. From that point of view, what we're doing here is basically redefining the constraint operator, right? So in a sense you can, the classical Hamiltonian is given by the lapse times the constraint operator, and in these two theories, in a sense, you would look at different constraint operators where you have made a different lapse choice. And so then, of course, these properties of self-adjointness are also different. I think this point was also made more explicit yesterday. And also, you can look at the path integral. And again, if you require unitarity, you will similarly require these different boundary conditions. So it really seems to just come down to this notion of unitarity or self-adjointness rather than any specific details of these quantization procedures. Because I'm in the black holes session, here's a comment that you can certainly generalize these things beyond cosmology. So that's one point I want to make. These arguments are very general. This unimodular formulation in the NO Teitelbaum version always has this preferred global time, if you wish. So you can also define this, for example, for the interior Schwarzschild de Sitter space-time. So this is your standard metric. You can see again this lambda as the integration constant of unimodular gravity. There doesn't seem to be a problem doing that, which then gives me this conjugate time, which is the unimodular time coordinate. I can write the metric in this unimodular time coordinate, and I see that the 3 volume, of course, would go to 0 at finite time. So I would have to impose boundary conditions. Presumably, I would resolve the singularity. So here's the summary. Quantum theories defined with respect to different clocks are clearly inequivalent if we require unitarity with respect to different clocks. And in a sense, what's interesting and also perhaps not appreciated often is that already the classical solutions give you an indication in a sense of where this behavior kicks in. And this is exactly where these solutions terminate when you write them in this particular time variable. And I wanted to focus on this case of the far future of de Sitter because this is really very low energy physics, right? So in a sense, this has nothing to do with singularities. So classical arguments we would think should be valid, but still you seem to be forced to have this drastic quantum behavior. Now, you might argue perhaps one of these choices of clock is in fact more fundamental, so unitarity should only apply to a specific class of clocks, perhaps, but then, okay, you have to kind of explain where that comes from. And of course, then, if we're looking at things like claims of singularity resolution on general quantum corrections to classical cosmology, which is the whole point of studying these models, these also then seem to be dependent on these choices. So thank you for your attention.
Thank you very much, Stefan. Also, thank you for keeping the time, which gives us the opportunity to take questions. You're the second.
So, hi, thanks for the talk. You basically started the talk with the statement that unitarity is inherent to quantum mechanics, but for quantum field theory on some, well, let's say on Minkowski spacetime, this also depends on your choice of time slicing, right? So, and in cosmology, I guess there is a preferred notion of time slicing due to the symmetries of the spacetime, but I don't see how in arbitrary setups there would be any globally preferred notion of time that would always slice into Cauchy surfaces, or where you could in any way expect unitary time evolution. Could you comment on this, perhaps?
This is obviously a very different setup, right? So here we're thinking of a quantum theory also of the gravitational degrees of freedom. The statement here I think is even much stronger than what you're saying, because indeed, in the cosmological context, there is a preferred foliation. But even then, just choosing different time coordinates, just in the one non-trivial direction that remains, already gives you these inequivalent theories. So the inequivalence problem seems to be even much worse in that sense. I mean, there might be reasons to require unitarity with respect to some choices of time or not, and I'm fine with that, but I mean, there's just a point here that you, in general, you do face this inequivalence problem.
Then there's a question by Steve up front.
So I'm a little confused already at the classical level here. I mean, of course it's true that you can always find a time coordinate that pushes singularities off to infinity. Usually we don't do that because that's not the time that's seen by a physical observer, in the sense that if an observer can reach a singularity in finite proper time, who cares whether the coordinate you've chosen says that it's an infinite coordinate time away? So have you looked at what happens just if you stick in a test observer and see whether that observer hits a singularity in finite proper time? Because surely that's relevant to picking out what time you want to be physical.
Yeah, so that's a common argument that often people make, and yeah, that I certainly see the point of that. I mean, here I'm following the philosophy of this relational program, which basically tells you, as far as I understand it, that you can pick a relational clock that has certain properties, and for example be monotonic, not have any turnaround points. And certainly the scalar field clock is very commonly used in models of quantum cosmology, right, as a relational clock. So here making the statement, what is the 3 volume of the universe as a function of this scalar field, this is very commonly used as an observable that people then quantize. And yeah, you might disagree with that, and that's fine. That's part of the discussion. Here I was just kind of following the consequences of what happens if we make that assumption.
I think that's excellent because it gives us something to discuss later on. So yeah, I think we should proceed with the next speaker. Let's all thank Stefan again. Yeah, so the next speaker will be Phil Simovic, and he will be talking about the relation between quantum black holes and thermodynamics.
Is that loud enough for the, Okay, thank you very much to the organizers especially for having me talk here today. I should try to stay in the yellow. My name is Phil. I'm a postdoc at Macquarie University. And today I want to tell you about some work that's been done over the past few years with my collaborators at the University of Waterloo and Perimeter Institute, whose names will show up throughout the talk, but also to just talk very broadly about the role that black hole thermodynamics plays in quantum gravity, the types of things that we have learned or can learn from studying black hole thermodynamics as they relate to various approaches to quantum gravity. So that's what I hope to accomplish today, and there will be later some focus on especially phase transitions for black hole spacetimes that occur in the bulk. So we have today lots of promising routes for understanding quantum gravity from a phenomenological perspective, tabletop experiments and avenues for probing quantum gravity features from cosmology, but nonetheless black holes remain one of the primary tools that we have and have used for the longest time in understanding especially non-perturbative effects that we expect in quantum gravity. And even at the classical level, they reveal many features that we expect from a quantum theory of gravity. And this has to do with their apparent thermodynamic properties. So for ordinary systems, we have thermodynamics, which arises as some coarse graining of some microscopic degrees of freedom. These seem to hold for black holes as well, which are presumably things we can interact with our own thermodynamic systems. So there must be some clues to these microscopic degrees of freedom contained even at the classical or semi-classical level that you can reveal by studying black hole thermodynamics. So whether or not the objects that we actually see in the sky in our telescopes today are manifestations of those classical solutions of general relativity that we're used to, nonetheless studying them tells us a lot about quantum gravity in general. So I want to talk about thermodynamics. So this will be familiar to some, but in the modern treatment, essentially black hole solutions obey a very nice law, which resembles the law of thermodynamics here. And it can be seen to arise really from diffeomorphism invariance of Lagrangian theories of gravity. So really in any metric Lagrangian theory of gravity, where the Lagrangian is constructed locally from the field and its derivatives, you can imagine you have some killing vector xi, some generator of your diffeomorphisms. There's some Hamiltonian that probably exists that generates the flow in your phase space that corresponds to that diffeomorphism. And then Hamilton's equations tell you that that variation is just given by some integral over a Cauchy surface of your symplectic current. Now, this holds generally, but if xi is a diffeomorphism and if you specialize to a black hole spacetime, then this is a pure boundary term. This variation vanishes, and you can write it as this integral over the interior boundary, which is like your black hole horizon, and some integrals of these quantities at infinity. Now, in the standard treatment, these are related to the surface gravity of the black hole and the entropy, which is this integral of this another charge 2 form in 4D. And this gives you the standard thermodynamic relation that was already derived in the 70s by just taking variations of the ADM mass in Einstein gravity. But this version holds much more generally for any theory that you want, really. There are some subtleties in the construction and ambiguities in the definition of these forms, but nonetheless, it holds quite generally. So the first lesson is A, that horizons play a central role in black hole thermodynamics. Whereas the temperature is something that has a little bit of leeway in its definition. People will scoff at the diagram on the left, and you should, because this is not really what we think of that quantum gravity will predict as a picture for a black hole evaporation. Nonetheless, this is the kind of picture that you would draw. You have an event horizon, and the temperature observed near Scri plus is related to the surface gravity of the black hole. But for the temperature, it's really not about the horizon, it's about the exponential redshift of the modes that come in with the collapsing matter. And this exponential relationship between the null generators at Scri plus and Scri minus is really all that you need to have a Hawking temperature, because this is the quantity that enters when you compute your Bogoliubov coefficients. So the temperature really doesn't have to do so much with horizons, and it exists in some approximate sense in spacetimes even where an event horizon never forms. But the entropy really does tell us something about the horizon, about boundaries. It suggests that really gravity admits this holographic interpretation. We've heard about this morning, and I'll cover some of the things that were said there as well, very briefly. But that's one of the main lessons. Gravity appears to be fundamentally holographic, and that really comes to light in the case of black hole entropy, which cannot be removed from the existence of that horizon. So I'm going to talk about phase transitions and what we can learn from those. And most of the studies of black hole thermodynamics take place in anti-de Sitter space. We heard this morning. It has some very nice properties near the boundary that allow you to define an ensemble where a black hole is in equilibrium with its own radiation, if it's large enough. So there is some natural length scale in ADS that separates a Minkowski-like region and an ADS region. This is Euclidean ADS, but nonetheless, a small black hole will act as if it's in flat space and just evaporate. The thermal state, the hot graviton state, dominates the statistical ensemble. But if the black hole is large enough, then it can come into equilibrium with its own radiation, which is reflected from the conformal boundary of ADS. And that's really just to do with the fact that the equilibrium temperature of the ensemble is not a monotonic function of the horizon size as it is in empty space, or flat space rather. So this is most salient in the Hawking-Page transition. It's easily seen by just computing the free energy using the ADM mass, the Hawking temperature, the entropy. And as you increase the equilibrium temperature of the space-time, for small temperatures, the radiation phase, or this hot graviton phase, whatever you want to call it, dominates the ensemble. But at some critical temperature, there is a first-order phase transition to a large black hole. There's also a small black hole branch. This one has a negative specific heat. This one is not thermodynamically stable, but this large black hole branch is. And this Hawking-Page phase transition has important applications in ADS-CFT because it's seen to be dual to these deconfinement transitions in various CFTs. And that's been studied extensively over the past 20, 30 years. So what we started to do was look at just more complicated spacetimes, things with more global charges and so on, with a variable cosmological constant, and try to understand what kind of structures emerge, what kinds of new bulk phase structure we can find that is interesting. There's a nice review by Rob Mann and his collaborators, and we looked at these Reisner-Nordstrom ADS black holes some years ago. And there, if you're in an ensemble where the charge is fixed, you can't have a Hawking-Page transition anymore, because if Q is fixed, then M can't go to 0. So instead what you have is the size of the black hole increases along the direction of the arrows, so you have a small to large black hole phase transition, much like the Hawking-Page phase transition, first order. If you have a variable ADS length scale, you can consider an ensemble where this is the extended phase space where lambda is variable. This will terminate at a second order phase transition for a given value of lambda. And you can draw the coexistence curve for these black hole solutions here. And they terminate at a critical point separating the small and the large black hole phase. And this has some remarkable similarities to what happens in ordinary fluid systems, van der Waals fluids, the liquid to gas transition. In fact, you can compute critical exponents near the critical point and find that they are exactly equal to the values predicted by mean field theory. So there's been extensive study of that in many different cases by lots of different groups, not just us. One thing we looked at a few years later was Gauss-Bonnet corrections. Okay, so leading corrections from some effective field theory description of gravity in the bulk. And you start to see even more exotic phase transitions, re-entrant phase transitions, we call them, where you're on this small black hole branch, you jump to an intermediate one, and then back down to a large black hole. A triple point where 3 stable phases meet and exist at the same equilibrium temperature. They contribute equally to the partition function there. So those are just some things that we've seen over the years. Now, with an eye for applications to cosmological spacetimes, flat space holography, de Sitter holography, we started to think about how to apply these techniques to de Sitter and asymptotically flat black holes. So it's a lot more difficult there because you don't have these nice properties of ADS. A black hole will just radiate, and especially even in de Sitter it's even harder because you have 2 horizons with an independent temperature. There's a heat flux between the 2 horizons. The system is not really in equilibrium. You can't define the asymptotic mass. You don't have a globally time-like killing vector field. And so there's a few different ways to approach it, but the most promising is one where you just fix data on a finite radius outside of the black hole. It's effectively putting it in a cavity, and the cavity represents the external environment of the black hole. And this is something that was done using a Euclidean path integral, originally by Gibbons and Hawking in the 70s, elaborated on by York and Whiting, and more recently, Steve Carlip and Vaidya presented a more modern treatment studying asymptotically flat and de Sitter black holes using this kind of technique, which we've since taken and extended to all kinds of different scenarios. So the basic idea is to take the thermal partition function and, in the standard way, approximate it. Well, it's some path integral that you can't do, so you approximate it in a saddle point approximation. You just take the dominant contribution to be the classical metrics which solve the equations of motion, and you assume that this can be done properly. This should be really the reduced action here. We work in spherical symmetry. There's a spherical reduction. And you work in this constraint subspace where you impose the equations of motion. You take this reduced action, and you can readily compute the mean thermal energy of the ensemble, the entropy, the free energy, and so on. And because you fix the temperature at the boundary, this really does represent an equilibrium situation, and you expect the first law to apply neatly there. You see all kinds of new and interesting type of phase structure in the bulk when you do this. I just give one example here because I don't have much time. That coexistence line that I showed before is now bounded in pressure at the top and the bottom. So it exists in just some compact region of your thermodynamic parameter space where ordinarily it's only bounded at one end. I should note that you have to be very careful about what it actually means when you do that Euclidean path integral, that saddle point approximation. Recently, Ted Jacobson and collaborators have elaborated on how you actually get to this saddle point approximation properly and how it can be done from the full path integral. And I think somebody will talk about that a little bit later today. So there are some caveats. Nonetheless, all the kinds of phenomena that you see in de Sitter with this cavity approach have analogs in anti-de Sitter where you don't need to use a Euclidean path integral at all. So we expect these kinds of features to be robust predictions, if not, precise numerical values that might change. So let me quickly talk about some kinds of things you can study through ADS-CFT, and there's various theories that can exist at the boundary that could be dual to the bulk. I'll just highlight some interesting features. I mentioned that we consider an extended phase space where you vary lambda, you allow it to vary, and you can see that lambda will actually, a variation of lambda corresponds to obviously a variation of the ADS length scale, and therefore a variation in the number of colors of the boundary CFT. Now this is a little bit concerning if you're motivated by ADS-CFT because now you're moving through theory space. So what you can do instead is fix n, but then you have to vary g in the bulk. So there are some subtleties associated with the extended phase space formulation as far as the bulk to boundary map, but you don't have to work in that extended phase space. You can just do things with constant lambda if you like. Corrections in the bulk, we have found, have implications for the boundary theory, which is S-strong coupling. So you can study some interesting things that reveal certain features of the boundary theories that you ordinarily might not have access to. One example, it's generally, so if you have an interacting quantum field theory in some IR limit, you can reasonably describe it with hydrodynamics. And for a very large class of such conformal field theories, the ratio of the viscosity of the fluid to the entropy density is a universal value 1 over 4 pi. So this divided by the entropy density. And corrections from the large n expansion only increase this value, so this is predicted to be a universal lower bound for this ratio for basically all fluid materials. If you add a Gauss-Bonnet correction to the bulk, then it actually lowers this universal lower bound in the boundary theory, and you see that it's actually less than 1 over 4 pi. So by studying these kinds of corrections in the bulk, we can learn things about the boundary CFT. So here are some examples that we studied over the years. Scalar fields with conformal coupling, 4D Gauss-Bonnet, Lovelock gravity, more recently regular black holes, and you can look at the papers there to find the details of that construction. So I close with, instead of avenues for future research, maybe questions for the discussion, things to think about. Black hole thermodynamics is not a solution to quantum gravity. It's not an answer, but it poses the questions that you need to answer. So where do the microscopic degrees of freedom live? Are they on the boundary of the black hole in infinity? What about information loss? Unitarity. Do we believe in boundary unitarity? ADS-CFT will tell you yes, other people will tell you no. There are arguments both ways. And what can you do in a local or quasi-local holographic setting? And how can you translate these results from this cavity approach to these notions of local holography? Those are some things that I would like to address in future work and discuss with whoever is willing. So thank you to the organizers. And
thank you.
Sir.
We do have time for one quick question for Phil.
Sorry for making you run again. So about these phase transitions of black holes in anti de Sitter. If I remember correctly, usually these heat capacity calculations, they don't really take into account the back reaction of the thermal equilibrium state of the quantum field onto the space-time as a whole, because this does not have zero energy, of course. This field. So have you taken this into account here in these calculations? Or?
So yeah, if you're very concerned about stability past this first order approximation, then you need to consider back reaction and do things like this. Just to leading order, we just compute the thermodynamic heat capacity and ignore back reaction. You ignore back reaction even when you compute this Hawking flux, so it would be a little bit inconsistent to start including back reaction effects in the one sense, but not in the other.
But it can essentially effectively change the radius of your anti de Sitter space.
It can do that, and it can also make an ensemble which is otherwise stable suddenly not stable. Nonetheless, even those unstable phases, they correspond to string stars in ADS and different unstable phases, but phases that you can still realize. I mean, even in an ordinary fluid, you can have a superheated fluid, and it's unstable, but it's still physical.
Okay.
Right? So,
thank you.
Okay, I think we should move on, but there's of course then discussion time. So let's thank Phil again. And then we have our final speaker, which is Sebastian Murk from Okinawa, who will talk about regular black holes.
Is this too high? Is that too high?
And also at least the first law of black hole mechanics.
Okay. Thank you for the introduction, and to the conference organizers for having me here and giving me the opportunity to share some of my research with you today. As already alluded to, I'm going to talk about the first law of black hole mechanics in the context of regular black holes. This is based on the work of a very talented PhD student, Ioannis Soronidis at Radboud University, and myself. So we have a paper on the archive with the same title. The paper has already been accepted for publication in Physical Review D, but it's not published yet. However, the latest version on the archive is entirely equivalent to the manuscript that we submitted, so there's no downside in reading the archive version of the article. Now, before I show you our results, I should explain what our setup is, so what framework we're working in and what our assumptions are. We're working in the framework of semi-classical gravity, and what that means is that space-time geometry, which is represented by the left-hand side of the Einstein equations, is still classical, and in particular that also means that classical notions such as the metric, such as horizons, such as trajectories of observers and of particles remain physically meaningful, and we can use them in our analysis. Now, what makes this semi-classical is that the metric is modified by quantum effects, and the way this is accounted for in the semi-classical Einstein equations is that instead of working with the standard energy momentum tensor of classical GR, one considers the expectation value of the renormalized energy momentum tensor in some quantum state psi. And so this renormalized energy momentum tensor encodes the entire matter content of the model. So in the context of black holes, it encodes both the collapsing matter and the quantum field excitations that it produces. I should also mention we do not make any assumptions about the matter content of the theory, about the style of energy conditions, about the asymptotic structure of spacetime, or about this quantum state psi. However, we do assume spherical symmetry, and a general spherically symmetric metric is specified by a line element of the form that you see here, where this function f is related to the Misner-Sharp mass, which is given by c half. So this is an invariant notion of the gravitational energy that's enclosed within a sphere of radius r. And this other function h that you see here is essentially an integrating factor in coordinate transformations, for example, between Schwarzschild and advanced null coordinates. We can always express the metric functions as series in terms of the coordinate distance from the outer horizon. And here, if you're wondering why there's no zeroth order term in the function for h, it's because you can always redefine your time variable such that this zeroth order term vanishes. And then we can describe general dynamical regular black holes by a function f that is the product of some for now unspecified function g times the coordinate distances from the inner and the outer horizon to the power of their degeneracies. So here A and B are positive integers where A labels the inner horizon degeneracy and B labels the outer horizon degeneracy. And I will also already note here, because it will be useful for later, that the metric functions C and H take on particularly simple forms at the outer horizon, where C is fully specified by the outer horizon itself and H vanishes. Now, many of you will be familiar with this 1973 milestone paper by Badin, Carl, and Hawking, where it was showing that a change in the gravitational energy is related to a change in the horizon area, and in particular it was shown that this proportionality factor kappa, which is called the surface gravity, determines the effective temperature of the quantum field on the black hole background. Now, if we use 4 pi r plus squared for the horizon area, then we immediately find the surface gravity is equal to 1 over 2r plus. However, it's important to point out here that the surface gravity kappa is unambiguously specified only in static or stationary spacetimes, where it's related to the Hawking temperature of the black hole via 2 pi th. And also this original derivation is for stationary black holes. However, because evaporation is a thermodynamically slow process compared to the overall evolution of the universe, what we should expect is that dynamically evolving evaporating black holes should match the behavior that is predicted by the first law in the quasi-static limit. Nevertheless, if we want to check this, then we need a proper generalization of surface gravity to non-stationary spacetimes. And people have already spent lots of time and effort looking for this, and there are various different proposals for generalizations. You can broadly categorize them into 2 classes, depending on whether they're related to what's known as the affine peeling surface gravity. So those are definitions that are related to the peeling of properties of null geodesics near the horizon. And the other class, which is the Kodama surface gravity, which is defined via the contravariant Kodama vector field and contractions with its covariant derivatives. And very recently it was actually showing that definitions that rely on this first mechanism of the affine peeling surface gravity are ill-defined for transient objects that form in finite time of distant observers, which includes evaporating dynamical black holes. And because of this, we focus on the Kodama surface gravity in our present paper. So to summarize the situation, you can say that in non-stationary, in stationary spacetimes, you have the killing vector field, which generates the null hypersurface that is the killing horizon. And then in dynamical spacetimes, this is in a sense superseded by the Kodama vector field, which is preserved in dynamical spherically symmetric spacetimes and generates this conserved current for any symmetric rank 2 tensor that is invariant under the spherical symmetries of the spacetime. And in fact, if this rank 2 tensor G mu nu is the Einstein tensor, then the current's Noether charge is just the Misner-Sharp mass. Now we want to evaluate the Kodama surface gravity at the outer horizon. So recall that at the outer horizon, H vanishes, so our line element simplifies, and also the Kodama vector field takes on this particularly simple form. And with that, we can use the generic form to describe dynamical regular black holes, and we obtain the following limit for the Kodama surface gravity at the outer horizon. And from this limit, we can see straight away that actually having a non-zero Kodama surface gravity at the outer horizon is only possible if the outer horizon is non-degenerate. So B, the label that we chose for the outer horizon degeneracy, has to be equal to 1. But we can also evaluate this expression without assuming this specific form that applies to dynamical regular black holes. So you could just use the definition of F in terms of the Misner-Sharp mass, and then you can obtain an explicit result by using the series expansion of the function C, and then you find at the outer horizon the Kodama surface gravity is equal to 1 minus W1 over 2r plus, where W1 is the linear coefficient in this series expansion. And this is really an exact result. So higher orders are not neglected here. They really do not enter this expression. Now if we combine this expression for the Kodama surface gravity with the first law, we can get an expression for delta M at the outer horizon. However, we can once again take the straightforward route because, as I said, the Misner-Sharp mass is nothing other than C half. So we can also evaluate directly and obtain another expression and then combine the two. And then on top of that, if you use the relations for area and volume, that allows you to relate delta R plus to delta V. And then you find this extended or generalized form of the dynamical first law. And then you can even go one step further and compare this with the traditional form of the first law of mechanics, and then you will see that the pressure term is identified explicitly by the linear coefficient of the Misner-Sharp mass. Now you also see from the results in the blue boxes that in order to recover the traditional form of the first law and the associated expression for the surface gravity, W1 has to be equal to 0. So in a sense, W1 being equal to 0 tells you if your model is compatible with the traditional form of the first law of black hole mechanics. And I should also mention that this is completely generic and applies to any dynamical black hole model, because on this previous slide here, we've used the generic form of F in terms of the Misner-Sharp mass, so we've not used the specific form that applies to dynamic irregular black holes. However, this is exactly what we're going to focus on from now on. So now we're using the specific form that describes dynamical irregular black holes. We're still using B equal to 1 because we want a non-zero Kodama surface gravity at the outer horizon. And using this, we can rewrite a consistency condition as an equation that involves the function G and the inner horizon degeneracy. And with this knowledge, we can test dynamical generalizations of popular models. So for example, the Bardeen model, which was the first regular black hole that has been proposed, the Dimnikova model, proposed in 92, and the model by Sean Hayward from 2006. So for example, we can consider the dynamical generalization of the Hayward model by allowing an explicit V-dependence of the horizon radius, the Schwarzschild radius, and the minimal length parameter L. And then what you do is you identify the roots of the equation F equal to 0. So this allows you to identify your horizons. In practice, this is done using a method known in the literature both as Cardan's method or Cardano's method, depending on which book you're looking into. And then you rewrite this function F in terms of these roots. And by comparison with the generic form that is valid for dynamical irregular black holes, you can identify the function G. And because we have an equation of our consistency condition in terms of G, and because the Misner-Sharp mass is actually also implicitly specified through FVR, because remember FVR is 1 minus C over R, we can evaluate this at the outer horizon and obtain an explicit expression for the linear coefficient W1. And you can see that this coefficient cannot vanish unless the minimal length L is equal to 0. But if the minimal length vanishes, then you no longer have a regular spacetime. You can also see if the minimal length is 0, then you no longer have an inner horizon. And you can follow those same steps analogously for other models like the Bardeen and the Dimnikova model, but because the results are essentially analogous, you will always find that this linear coefficient cannot be 0 unless L is 0. I will move on and show you something else, which is the degenerate models of dynamical irregular black holes. So these are models where A is not equal to 1, but A is greater than 1. And here one usually makes two additional assumptions, which are well motivated physically, but I won't have time to explain why. But you don't have to trust me. You can look in the papers by Frolov and Caballo, Lubio, Di Filippo, Liberati, Pacilio, and Visser. So the first assumption is that this function F decomposes as a rational function of the radial coordinate. So here Pn and tilde Pn are polynomials of the same degree in R. And then an additional assumption that is made in this JHEP paper here is that G decomposes as something that is 1 over a polynomial in R. Now with these additional assumptions, we can again rewrite the consistency condition as something that involves these generic coefficients. And here we can actually, we know what the generic form of these coefficients is based on dimensional grounds, because the only relevant length scales are R minus and R plus. So this generic form is prescribed purely based on dimensional grounds, where these coefficients Dij are dimensionless. And then, admittedly, I'm not going through the full derivation here, but what we show in the paper is that you can actually rewrite this again as a condition that involves nothing other than these dimensionless coefficients and the inner horizon degeneracy A. And this is something that you can evaluate not generically, because in principle you could have infinitely high A, but in practice when A is known, you can usually evaluate this explicitly. So for example, for the model that was proposed here in this paper, A is equal to 3. I should also mention the reason that this model was considered is because it can cure the mass instability problem that typically plagues dynamical regular black holes. So here in this particular model, A is equal to 3. And again, I'm not going through all of the steps here, but what we find in the paper is that this condition is satisfied if and only if this particular polynomial is negative. However, you can check by looking at the discriminant that it'll always have two distinct complex conjugate roots, which tells you that this polynomial is in fact not negative but always positive. So we get a contradiction. So to summarize, we've looked at the first law of black hole mechanics for dynamical black holes, and more specifically regular dynamical black holes. And we've seen that the first law receives generic corrections which correspond to an additional work term. And we've also shown that the linear coefficient in the Misner sharp mass actually suffices to fully specify the thermodynamic properties. And lastly, this is something I haven't talked about so much in this talk due to time constraints, but we also show that this need for corrections for regular black holes is inherently linked to the introduction of a minimum length scale that is needed to regularize the space-time. And there are also some additional results in the paper that I didn't have time to go into today. So for example, we also considered the dynamical generalization of the charged Frolov black hole. We also outlined and discussed implications for page evaporation. So if you're interested, this is the QR code for the paper. And also if you're watching the recording later, please feel free to email Johannes or myself. And with that, I think we can open the floor for questions for people in the room. Thank you.
Thank you very much, Sebastian. And yeah, indeed, we have time for some questions before we proceed to general questions. Let me just start while people are still thinking. So you have this dynamicalization. Are you sure that it's the unique process of taking a regular black hole, or are there different ways of finding dynamical models?
Yeah, that's a good question. So as far as I'm aware, any regular black hole model that is dynamical you can cast in this form. However, we did receive one email that there is apparently a regular black hole model that only has one horizon. So we have yet to look into that and see if we can do that with the same functional form of F.
Yeah, there's one more. And I can already ask the other speakers to come.
Thank you for your talk. So this Frolov black hole is the one with the limiting curvature assumption, right? Is that
so if you look at the Frolov generalization, yes, but we looked at Hayward. But there is a charged Hayward-Frolov black hole as well, which we considered in the paper, but which I omitted due to the time constraint in the talk.
Okay. So I just wanted to see if
it's this one here, where these are the two main differences here.
Oh, okay. Because they have a bound on basically on the curvature. That's their conjecture. I wanted to see if the corrections that you showed in the last slide have any direct relation to those upper limits for the curvature.
So you're asking if this is related to the limiting curvature bound?
Yes.
That's a good question that I don't know the answer to. But yeah, thank you.
Okay, so before we proceed to the more general discussion, let's thank Markus again. Sebastian, sorry, I'm sorry. And then I think we already have a question for Stefan. So I'm going to first call for more remaining questions to the speakers from the audience.
So Stefan, suppose you want to figure out models, whoever claims that, okay, there is a singularity resolution, let's say look LQC, okay. So suppose you want to figure out whether that is due to a choice of lapse or due to the choice of the quantization or the lattice. So how would you go about it? I mean, do you already have some results or intuition, or if not, what would you do?
I mean, one thing to do would be to try and redo the same quantization using a different clock, right? I mean, that's an obvious starting point. So in loop quantum cosmology, I mean, you mentioned that all of the literature is based on the scalar field that I also had here, the massless scalar field. It's always that which is the clock. So if you were able to write down a model that had two possible clocks, maybe a perfect fluid or unimodular gravity, and you use the other one, you can compare whether you get comparable results or not. And I think that would be the starting point.
Okay, and what seems here is that you always have to have a potential for the scalar field which allows you to have a monotonicity in the phi or pi, right?
It's a free scalar field, so the potential is exactly zero.
Oh, you don't have a potential.
No,
okay.
In fact,
so you can't have a potential. Is that okay?
Yeah, I mean, there's people in this room who know more about this than I do. I mean, there may be particular fine-tuned choices of potential that still allow, identification with the clock, but in general, yeah, you lose this monotonicity property, right? Because if you have a potential, a scalar field can turn around, and then it no longer serves as a clock.
There's a further remaining question for some speaker.
Okay. My question is not really for any speaker in particular, but just a general question. And in fact, it's a bit philosophical in nature. So the question is, why do we want unitarity in quantum gravity to begin with? I mean, one can ask this question for quantum mechanics, basically, because people often quote probability conservation that implies unitarity, but this is not true. I mean, it's not. Unitarity is an independent statement. So why would we want to construct a quantum theory of gravity that obeys unitarity to begin with? And do we really want to do that or not?
I think that's a very broad question for this session, but if the speakers have a go on that.
So at least from my point of view, I mean, I don't do asymptotic safety or spin foams or anything like this. Most of my contact with quantum gravity is through ADS-CFT, and of course there you naturally expect unitarity because you believe you have boundary unitarity. So if your boundary theory is unitary and you can reconstruct the bulk entirely, then quantum gravity is unitary. Now, there are some arguments, people go back and forth. Don Marloff gives some arguments for why you should always have boundary unitarity, but I think those arguments rely, the central thing that's missing is, he shows that whatever observables you have at one time on the boundary, you can reconstruct at any other time. So it's unitary in this sense, but that doesn't mean that you can fully reconstruct the bulk. That requires some subtleties involving doing the sideways Cauchy problem, reconstructing a field point here using data on the time-like boundary. And I think it's not clear if that can always be done, especially in spacetimes which are not causally nicely behaved. So, but from other approaches to quantum gravity, I'm not sure what the answer is.
Can I just, maybe I can just comment. I mean, okay, if you do ADS, then unitarity is natural thing. But if you have a holographic approach to gravity in general, then you can have a holographic relationship between two non-unitary theories. So, I mean, that can also be, I guess, studied when the boundary theory is not a conformal field theory. Right? It's not need to be unitary either way. So my question is more along those lines. I mean, do you really need to impose unitarity in some way? But I understand it from the ADS-CFT construction, it is automatically unitary, so that's okay.
I mean, I think we've seen a few talks here and some different approaches where you can show that there is unitarity, but it's not built in, it's not required. So if that is something philosophically you disagree with, you can, I suppose, abandon it and examine the consequences. But
it would certainly make things more complicated. I think that we can all agree on. Let's maybe proceed with some. I think there was one comment. Steve? What? You want to comment on unitarity? Yeah.
A couple of comments on unitarity. First, why? Well, people have tried to parameterize the kinds of departures from unitary evolution that, for example, would be suggested by non-unitarity and black hole evaporation, and it leads to a disaster. This is work of Banks, Peskin, and Susskind, and various understandings that are part of the lore going beyond that. You end up with violent violations of energy conservation that would be in disagreement with pretty much everything we see. One other comment on unitarity related to Stefan's talk. Of course, trying to formulate unitarity in terms of these relational clocks is subtle business, I think, is part of the message. But there is a sharp way, or a sharper way of looking at unitarity, I think, in quantum gravity, and that is to look at unitarity of the S matrix, to consider, asymptotic data, say, perturbing about a state that corresponds to asymptotically flat spacetime, or also possibly ADS, where you have a nice asymptotic region, and really ask there the sharper question about unitarity of the S matrix. And of course, when you get into the ultra-Planckian regime, then you make contact with the issues you have with black hole formation and Hawking's arguments, etc.
Thanks. If someone wants to, otherwise I would try to get this more closer to black holes again.
Okay, so this is for David again. I'm just trying to understand the model better. So from what I understand, your principle, of course, is keeping or having the hypersurface deformation algebra, that you start from that principle, and the model in principle has nothing to do with the quantum gravity. And then you want to preserve that, and then you go on and introduce the general form of Hamiltonian and do the rest of the machinery. Okay, so that's one I wanted to know. And the second thing is that you mentioned a horizon there.
Yes.
Is that an event horizon or an apparent horizon?
That's an event horizon, yeah.
An event horizon. So
yeah, from an external observer, would be similar as the classical Schwarzschild horizon.
Okay, so even after the manipulation and change of the Hamiltonian constraint and everything, you still have an event horizon, not an apparent horizon. And it's null and all that stuff, right?
Right.
It's not, okay. Because there are models where they have two horizons after modifications due to loop quantum gravity.
Okay.
And the inner horizon is not null always, yeah.
No. We have just one horizon. We have afterwards the white hole horizon, but this is like, yeah. It's the same horizon, it's R equal to M. And for an external observer, it will be an event horizon, yeah. We can define it in the asymptotically infinity, yeah.
Okay, thanks.
Are there more questions, or maybe do the speakers have a? Oh, there's one in front there.
But I mean, when you're changing, you're no longer in GR, right? So do you still know that light is the speed limit for everything? I mean, how do you know you have a horizon? And usually, if you look at what dictates the causal structure? Are you still sure that nothing exceeds the speed of light?
As I define horizon as a Killing horizon. I have a Killing vector field, which is null there.
Are they causal processes which will bring you outside? Since you're no longer in GR, it's not clear that what these characteristics are.
Yeah, but I mean, we do the study, the precise study of the maximal extension, and this is the picture I show you. And there you can see, I think, from an external point of view, it's the same as GR, an external observer.
So I have a question for David. So I was wondering what your perspectives are for model building of sort of modified black holes, because this is obviously a big business at the moment. And your results, I mean, seem quite restrictive in the end, right? That once you impose a certain set of assumptions, and maybe you require, for example, that the curvature doesn't blow up far away from the black hole, which seems quite disastrous, you don't have many options left. Is that a fair assessment? And if yes, how is your perspective for how we proceed with this modification of classical black holes?
Yeah, I would say that it's quite restrictive, but also the ansatz we started with is based on the classical Hamiltonian in a sense, right? I mean, you can add, for example, higher derivative terms. And we see from this ansatz, for example, that it's not allowed to polymerize the KX. There is a connection component which is not allowed if you apply these requirements. And then you can work out, I think, higher derivative corrections, which are expected at the end of the day in some quantum gravity theory. And on the other hand also, I mean, it's quite restrictive in a sense, but still you have, I think, 5 or 6 functions of the radius that you can play with. I mean, this also can give you a lot of room, I guess, for different space-time behavior. But yeah, I think it's quite restricted.
This was actually one of the questions that I still had to your talk. The 5 functions, they are still in general free, so you make then choices, right?
Exactly. That's what I do later. I do, like what I was saying, the minimal deformation, in the sense that I take what I consider the closest thing to GR. But yeah, you can play with that a lot. And yeah, I mean, you need some external input to choose those functions, yeah.
More questions, yes.
I have a question for Stefan. I was wondering, in light of your goal of resolving the cosmological singularity, what do you think is the relationship between your approach and Hawking and Penrose singularity theorem? So, for example, other than unitarity, do you need to assume any energy conditions on the scalar field?
Yeah, so of course what I'm showing here is just a purely quantum version of singularity resolution, right? So I'm not sure I can see really much of a connection to those theorems, which are classical, obviously. I mean, I know there are people who try to extend these singularity theorems into the semi-classical regime by sort of making the stress energy quantum, for example, in semi-classical gravity. Maybe one could go further in that direction. For me, it's not clear what the connection is. I can't tell you what the connection is, because this is just, here you have a quantum state for the metric and for the matter fields.
I actually still have a question for Phil, if there's currently no other. And that's, you presented the thermodynamic argument as being very general, and I understand that there's a derivation which makes at least very little assumptions about the dynamics that underlies the solutions. But in how far do you know that the thermodynamic stability aligns with just classical stability?
So when you say dynamics, do you mean dynamics of the classical solution that you're considering, like the black hole itself?
Or dynamics of a particular
because there everything is assumed to be stationary, and there's no.
Yes, but then of course, I mean, for instance, in GR we know that black holes are classically stable, right? Mm-hmm. So, but then the first order effect is thermodynamics. But that need not be the case in a theory beyond GR. There can be classical instabilities, right?
True.
And I know that in many cases thermodynamic stability and classical stability align, but I was wondering, because you looked at a large class of theories, whether that's always the case or...
So in those, stability was usually manifest, but it's because we're fixing data in a finite radius. So in de Sitter it's easy. It's fairly straightforward to get stability. Maybe you don't have it for all the different black hole sizes, but there's usually some region in your parameter space that corresponds to stable solutions. This is not the case in asymptotically flat or ADS spacetime. Now we don't really look at corrections past what the saddle point approximation to the path integral just gives you the leading order. I mean, it somehow knows something about the entropy and presumably things that are subleading, the quantum effects. But again, we're not doing a full path integral, so we're not really sensitive to those kinds of things. So if there is an instability that develops at higher order, you would need to have higher order contributions there to see that. But I'm not aware of let's say, kind of a systematic approach that's been done at looking at stability from a higher order loop expansion in the path integral.
No, but I don't mean going higher order in loop expansion. I really just mean that I would expect actually that if you have a particular black hole solution, I can sort of find an unhealthy mode that I can additionally write down in dynamics that really creates a classical instability where you would conclude that the thermodynamic stability is...
Yeah, but here also we're working in spherical symmetry, so you're kind of restricted into what kind of perturbations you can do on the black hole. So I think as far as classical perturbations go, you only have spherically symmetric modes that you can consider. And some of the solutions are unstable, even thermodynamically. Many of them are. And that usually does correspond to the classical instability. It's just not always the case. But I haven't studied the perturbations of these solutions very much, so I can't really comment more.
Okay, thanks. Okay, if I don't see anything from the audience right now, I still have one more thing, which might be a nice closing. So almost everything that we've seen today was spherically symmetric. And even in GR, we kind of know that the step from spherical symmetry to axisymmetry does a lot of new things, right? We know, I mean, at some point, I think that spherical symmetry was regarded as an artifact, that the black holes in spherical symmetry were regarded as an artifact of the high degree of symmetry. So in how far do you expect things to really change drastically as you, with your particular model or theory, go to from spherical symmetry to axisymmetry?
I don't know, but I really will expect a lot of different behaviors there. Yeah, I mean,
you wouldn't?
I will expect some differences. Yeah, but I have no clue.
Yeah, I will counter that. So I'm part of a group that works predominantly with quasi-local horizons, and there you actually see that in spherical symmetry, if you have a quasi-local horizon that forms in finite time with a distant observer, then this black hole should not be able to accrete mass after the horizon has been formed. So it can only evaporate, which is because you have the presence of firewalls which violate bounds on the NEC and all of that kind of stuff. So here it would really be interesting to see if things change in axial symmetry, because if they don't, then we're sort of running into conflict with experimental data, because from EHT we see accretion disks. Of course we don't know for sure whether or not there is a horizon, but I'm not aware of any mechanism where you can have continued or sustained accretion very close to the horizon without actually crossing it. And similarly from LIGO and Virgo, we've seen merger of black holes, and then the resulting black hole's mass is bigger than each of their progenitors. So if these objects truly have horizons, then somehow some mass must have been acquired and some horizon must have been crossed. So yeah, it would really be interesting to see, and I'd be surprised actually if, at least in the quasi-local dynamical case, there were no differences.
So I'll just quickly say, from the perspective of black hole thermodynamics, I mean, rotating solutions, angular momentum is very easy to incorporate. It's built into the first law. It does significantly alter, in many cases, the phase structure that you see in the bulk. Anytime you have more global charges, you have more potential solutions that can dominate the partition function for given values of the angular momentum or charge or whatever. So it does have a big effect, but it is naturally incorporated there. However, when you're in asymptotically flat or de Sitter space-time, if you're doing this kind of cavity approach, it's a little bit subtle. How do you fix the temperature on the cavity? Because that's not spherically symmetric anymore. And so do you use zero angular momentum observers or something else? And it's not clear that you can always have just one temperature assigned to the surface of that rotating cavity without having other issues. So.
Okay, I think unless there's urgent reactions, comments, question, or whatever, I will not keep you from the coffee break. I think the next session proceeds at 4, so in 30 minutes, and we can all discuss further.
Okay. Last session. Our first speaker is Laurent Freidel, who's going to talk about quantum geometry and entanglement from corner symmetry.
Okay, thank you. I want to thank the organizer for this beautiful conference, very diverse, and the opportunity to speak here. I also want to mention, here I'm going to give a bit of a summary of many ideas that we have been developed with many. I was lucky to have many bright collaborators, and for people who are interested, some of these ideas are kind of summarized, more for a quantum gravity audience, but as you'll see, some of these ideas are very general in some way. So if you want to have a look. So the main, one of the questions I'm interested in, like many people in quantum gravity, are really what are the fundamental degrees of freedom. But what I want to do is kind of propose a new way to look at quantum gravity. Instead of having a top-down approach where I postulate what is the fundamental theory, I kind of want to have a more like bottom-up approach, which is rooted on, let's say, semi-classical physics, maybe non-perturbative in G Newton, but trying to understand really the essence of what is the nature of the constraints due to gravity, and it turns out that there's a very very fundamental question that allows you to go a long way, which is really. Essentially, what is the nature of entanglement across subsystems, or something that in fact we don't completely control, which is how do we quantize quantum field theory and gravity on finite regions? And I think we want to understand finite regions quantum systems because, in some sense, the smallest one, where this is the quantum gravity point, the biggest one, it's the S matrix. So this is a good intermediate between the two. The idea, that can organize that is local holography, and you can view it as a fusion of some of the key idea of holography with some of the key idea of quantum geometry, that the geometry has to become quantum, represented by quantum operators there. So now, of course, in holography, the emergence of classically connected spacetime is already due to the nature of entanglement, so that's why it's interesting to look at it. Now, what we're going to show, and if you fall asleep in the talk, at least I want to make my main point here. What we're going to show is that in gravity, something special happens, that the subregion entanglement is entirely controlled by a symmetry group that we call the corner symmetry group. That group is universal, and I'm going to show you what it is, and then we're going to study a bit some of its property. And this symmetry group just follow from the expressions of the gauge invariance. So in some sense, if you break gauge invariance, you're not going to have the symmetry, but the presence of the symmetry is a necessary condition for you to be able to reconstruct a space which has the gauge invariance. And then at the quantum level, now that we have a group, we have the job of trying to find and classify its representation, and finding the quantum representation of that group amounts to getting towards a picture of quantum geometry. And so the main point of the talk is to essentially show that entanglement in gravity is equivalent to corner symmetry. Entanglement is a very vanilla thing in quantum mechanics, but when you have a symmetry, there's a charge conservation that has to happen across the link of the entanglement. And one of the purposes of holography is somehow to show that this symmetry is so strong and so large that it controls all of the entanglement. And so what this allows us to do is get a picture which is not a full picture of quantum gravity, but it allows us to go from the continuum to some kind of a quantization, to a precise quantization of geometry through the quantization of the charge of symmetry. And symmetry is the one thing that we know to quantize without any too many ambiguities. And then what it also shows is that recent work have shown that, I'm going to talk about quantum gravity in a bit, but I've used these techniques a lot to talk to people in celestial holography where the corner is very big. And here we have much more control and perturbative control onto what it is. But the beauty is that now there's no distinction between people doing, or at least we have a common language between people doing the S matrix and people doing quantum geometry. And for me it's very fruitful because then you can use the different insights and techniques between the two. So what's the main problem? The main object I want to study is the quantum causal diamond. So usually it's a Cauchy slice, which I call sigma, and you decompose this Cauchy slice into, left and right. Okay, an interior and exterior, and there's going to be an entangling surface. That's what I call the corner S here. And then, of course, you know, in a fixed background, you can shine light rays out of that, and you get a causal domain of dependence. That's your quantum causal diamond, which, of course, is going to fluctuate in gravity. So now, you know, usually we assign the algebra of observable associated to the slice sigma and maybe the slice sigma L. And then we want to understanding subdivision is you want to understand how does the system, the quantum system behaves when you subdivide, when you make this subdivision. So if you're in quantum mechanics, which is quantum information, then, you know, it's very nice because then you have the algebra of observable decomposes as a kind of a union of local algebra of observable associated to the left and to the right, and that the Hilbert space also decomposes as a tensor product. So we are in condensed matter, quantum information, everything is nice, and we have a beautiful way, and we can assign density matrix to subregion because of that. Now, in relativistic quantum field theory, the first problem arises that we lose the factorizability of the Hilbert space. So the Hilbert space attached to the total region cannot be written as the tensor product of Hilbert spaces attached to each subregion. For the observable, it's okay. You still have a notion of local observable, but there's no notion of local states. And the reason behind that is that you know, you have universality or entanglement at the region. The Hadamard are property of the vacuum states, and therefore you have infinite vacuum entanglement. So you lose this factorizability. Another way to see that is that, you know, in non-relativistic quantum field theory, if you have the states attached to the left regions or to the right regions, they kind of are orthogonal to each other, but in quantum field theory, they are not. And this is the Risch-Leader theorem, right? The fact that you can manipulate something very far away just because of this fundamental vacuum entanglement. And this vacuum entanglement, it's UV divergent, otherwise it would not be, it would become factorizable. So this is really the object that we are after in quantum gravity. This is the one that bugs us, the fact that somehow we lose factorizability, so we really have to face that. This is UV divergences. And it means you cannot define the notion of density matrix attached to subregion in quantum field theory. Okay, so now in gravity, in fact, the non-local, it goes even beyond, because in gravity, of course, it's a field theory, so we don't have factorizability of the Hilbert space, but we don't even have factorizability of the observable, the gauge invariant observable now are because the observable have to be gauge invariant. And if I have gauge invariant observable on the region sigma L and gauge invariant observable on sigma right, I'm still missing some observable, which are going to be the one which are Wilson lines across, for instance, the left and the right. Okay, so clearly there's something interesting. So, you know, as much as in the literature people went from quantum mechanics to quantum field theory, and there's an infinite number of papers about that, and the type 3, etc., there's very few people that go from quantum field theory to gauge and gravity, and this is what I want to focus on. Okay, so what's happening here, I mean, clearly we have to kind of be able to deal with that. We want to be able to understand what is the decomposition of observable into subregions, and if we can talk about quantum states associated to subregions. And of course, to recover quasi-locality, the idea is that you need to introduce a physical system, which is the dressing of the states. And to understand what the dressing of the states are, you need to understand what symmetry control this dressing. So this is the idea. So why is symmetry so important? Well, in gauge theory, as you all know, the main aspect, and let's focus on gravity, when no boundary exists, you know, if you try to compute what is the Hamiltonian of the system, well, it's simply a constraint, so it's zero. So-called problem of time. Okay, so the time evolution generator is always zero in gravity if there's no boundary. Now, the situation changes in the presence of space-time boundary or space-time corner. And I'm going to distinguish the two. So a boundary is a codimension one object, and a boundary requires the boundary conditions to be defined. We saw that in ADS-CFT, you have to put reflective, otherwise you don't know what you're talking about. You cannot define Hilbert space. Now, a corner is very different. A corner is codimension 2, and the beauty about a corner is that I don't need to impose any boundary condition to define what I mean by field theory on a corner. Okay, and it's very important because I don't want to have to impose particular boundary condition because I want quantum gravity to decide for me exactly how things are going to fluctuate. Okay, so corner is a boundary of a slice, but it's not a boundary of space-time, and I don't need boundary conditions for corners. Okay, so this is a corner. The corner is just the endpoint of this causal diamond, and now in this presence of this corner. Going back to Emil Noether, that's what she proved, asked by Klein and that's the one paper she wrote in physics where she really showed that in the presence of boundary, the Hamiltonian is a pure corner term, and she computed that term in GR in 1918, and then we kind of forgot about it for I don't know a long time. So it's due to Emil Noether that we know that we can write this object like that. Often people cite Lee and Wild and people like that, but you open the paper of Noether, it's all there. All these formula of Ayers, Wild, etc., they're already there. Okay, so as I say, corners unlike boundary do not need a specific boundary condition. Now, why is it interesting? Essentially, it goes back to Don Marolf and maybe others that when people were trying to understand what is the conceptual nature of holography, well. They were saying that they were wondering, well, here it is. The energy of a total system, and then was doing it in the case of boundary conditions where you have conservations of energy, and then here you conclude from the Noether theorem that the energy of the system is completely determined by data on the boundary. Okay, that's kind of so that this property, which is essentially the property of gauge invariance, is also the other face of gauge invariance in simply holography. Okay, and so what we did with William is just, extend somehow this notion of what we call local holography to any kind of a cut you can put on a slice, because it's always really trying to see how far you can go. Okay, so now this. So now what do you have? You have many gauge transformations here that will have vanishing charges. These ones are gauge symmetries. And then there are some transformations which have non-vanishing charges, and these ones are not gauge symmetries, they're going to be the symmetries of your subsystems. And because they're symmetries of your subsystems, they're really physical objects that you need to quantize. So this group of symmetries here is what we call the corner symmetry group. And then one of the main items that is coming to the forefront now is that the modular group, which is really the group of, in gravity, the group of modular transformation, which is kind of the statistical group of symmetry due to subregion, is just a subgroup. It's a particular subgroup generated by a Casimir of the corner symmetry group. So somehow, that's why the corner symmetry group is also important. It's a symmetry group, but it's also part of this kind of it's part of the modular group. But the modular group is a subgroup of the corner symmetry group. So the Noether theorem tells us that these charges, satisfies an algebra. Now we know that the charges also can be represented in terms of the metric variables. So the Noether theorem tells us that some component of the metric, particular component of the metric, after I have imposed the constraints, are specifically non-commutative, and this is something you can prove in the continuum. So it means that the non-commutativity of these metric components evaluated in the corner is really a non-commutative geometry that you're dealing with. And therefore, finding the representation of this corner symmetry group is equivalent to to quantizing geometry or some element of quantum geometry. So I hope the project is clear. Okay, so so let's do gravity. By gravity, I mean the theory of purely metrical. So we look at the region R. With a boundary, so in a slice with a boundary S here, which is the untangling sphere. And now, as I said, the corner symmetry group, or the extended corner symmetry group, is the symmetry group of diffeomorphism transformations, which have non-vanishing charges. And so what you find is that in metric gravity, this group is made of three parts. So first, of course, it contains the diffeomorphism along the sphere. So think about the sphere. We're going to go there. The sphere is a kind of a fluid, and you can move along the sphere. Then there's a SL2RS, which means per point on the sphere, there's a possibility, you have two null direction, and you have a possibility to do boost in this two-dimensional plane here. And then in general, and then there's also two null directions. You have the possibility to do super translation. So often people call that super rotation, super boost, and super translation. And I'm going to focus on the blue part because the supertranslations are different. They kind of move one slice to the other, and I have to be able to compute the flux. But first I want to understand some of the kinematics. Like, think about taking a snapshot of geometry at a given time, and I want to know what are the elements, what are the constituents of the geometry, and then of course how they evolve in time through the flux and how these charges couple to gravitational radiation. Here we're going to spend more time in the first part of the project. So now, something which is extremely important is that this group is doubly universal. So what I mean by doubly universal is that it's the same group whether you have a small s or a big S, a round S, or a wiggly S. It's not that it's only true for the black hole horizon. It's true for any cut. So whether it's an infinitesimal one or an asymptotic large one. And then also less obvious, which was proven by Speranza, based on work by Well. This group is the same no matter what is your action. That is, you can take Einstein-Hilbert or any higher derivative corrections. You're going to get exactly the same group of symmetry. What's going to change is the canonical representation. So it tells you that, if you think of quantum corrections as adding higher derivative, you still have to represent the group. And I think what it means for me, it means that whatever is your theory of quantum gravity, and I don't care where it comes from, at some point, at some level, you have to find a representation of that group. Any theory of quantum gravity, or if it's not a representation exactly of that group, you have to tell me, well, that group is deformed by the Planck string or the string scale or whatever, but you have to go back to that, because if you don't find that group, you are fundamentally breaking diffeomorphism invariance. Which, okay, maybe if it's your option, then we won't talk. And the beauty is that here, you see, it's very theory agnostic. So we should all agree that whatever the theory is, in your theory, you should be able to do that calculation and get an answer for what this object here. So, okay, so that's why I kind of like it. In the sense, it's kind of a firm ground in which you can stand and build a much more fundamental picture of geometry. So, okay, so usually maybe you have heard about symmetry group at asymptotic infinity, etc. Okay, so here an equation is missing. I just have the group I was writing before here. This is the group I was writing before. Now, of course, I can look at a subgroup that preserves a null direction, and it's the symmetry group of null surfaces, which was well known, which we call BMSW. So this is something that was identified in the literature on horizon, an isolated horizon, dynamical horizons. But it's also the group of symmetry that happens at infinity. So it's not like there's zillions of different symmetry groups. There's only one symmetry group that you have to represent, and then if you go to infinity, you just represent a reduction because you have a preferred null direction. Okay, so it goes back with this universality of what the group is. So the study of this representation theory for final group, feeds the one at infinity and vice versa, in some sense. So BMSW, and here in BMSW, you have a null direction here. What are the infinitesimal generators? Very simple. You have a super translation. You have a tangent vector in the coordinate where A, and then you have the Weil is kind of this boost, which is very important. And at infinity, okay, an equation is missing again here. The W, what happens at infinity is that this Weil factor is proportional to the divergence of the vector field because of the conformal structure. Okay, so that's the group. And then, okay, so if you have a group of symmetry, and I'm not going to give you exactly the formula how it relates to the metric components, but you want to understand what are the representations, what are the Casimirs of this object. Now, it's a semi-direct product. If you remember something about Planck array, SO3 acting on R, you know that the representation theory are classified by the little group representation. So what are the little group? So the first thing you have to appreciate is that you want to understand what is the Casimir of SL2R. And the beauty is that in all the model you can imagine, the Casimir of SL2R is simply the area form on that sphere. Okay, so and you can understand geometrically what is the subgroup generated by this Casimir. It's really, if you have a null surface and I give you a metric, if you have a surface I give you a metric, there's two preferred null directions. which are the directions where these normal vectors are null for that particular metric. And then, of course, there's a preferred subgroup, which is the subgroup that preserves that null plane. This is the group generated by delta V. It's the group of boosts, okay, along the null plane. So this area element is the local affine boost group, if you want. And now, what is the little group? The little group is the group of diffeomorphism that preserves that Casimir. So it's the area preserving diffeomorphism group. Okay, and locally, Arnold and all the Russian mathematicians have developed the theory of representation of this group. So it's kind of well known, maybe not as well known as the Virasoro group, but there's a lot of literature where you can use to quantize. So and physically, in fact, this group of symmetry, when I replace SL2R by just functions, and I think of square root of G as a density, is really the group of a barotropic perfect fluid. That if you quantize, you get helium-4 in 2D. If you quantize it in 3D, you get helium-4. Okay, so the error-preserving diffeomorphism group has a generator, which is the vorticity, and then, okay, you can construct, essentially it's the fluid vorticity. What I'm saying is that you have a diffeomorphism generator, so you have a notion of momenta generator. You can compute the vorticity of this momenta. There's some decoration to the fact that it's non-abelian. You can prove that this object satisfies the area-preserving algebra. And then the Casimirs of this algebra are simply these moments of the vorticity here. Which is something that is used in predicting the weather on the sphere. The Casimirs are exactly the things that do not change very fast, even in this chaotic system. And that's how we can predict the weather for a few days. Okay, so here we have a complete classifications of representations when the area form is strictly positive in the continuum. Now, okay, so let's talk a little bit about edge mode. Of course, here, there's a bit of a certainty in quantum gravity. So which surface am I talking about? How am I going to place a surface in space-time? Well, in order to do that, I need you to give you a field where that surface is. And this is what I call an edge mode field. Now, in field theory, it's kind of simply a coordinate, and it's completely decoupled from the phase space. But in gravity, it is not decoupled from the phase space. So the edge mode variable are kind of physical in the sense that, like our 4 edge modes, 2 are transversal and 2 are longitudinal, they are promoted to operators. Here, sigma is the position on the sphere. So what you have is this kind of 4 operators associated with the sphere, and they are kind of necessary to define the locations of the sphere in a different invariant way. Okay, and of course, because they're operator, they need to fluctuate, so it's perfectly consistent with your notion that, it's kind of hard to precisely locate a sphere element here. So now what the edge modes allow is, okay, here I'm going very fast, the possibility to define gauge invariant observable, because you can use them to dress your observable. And what it does, and this is the construction we did with Anthony in 2016, we constructed the algebra of gauge invariant observable, which contains, the naive algebra, and then there's a wedge product here with the algebra and the boundary. It turns out this algebra has a mathematical name, it's called the cross product algebra. And so the extended algebra we constructed is simply the cross product algebra with the symmetry group. And now recently people have been excited about the cross product algebra because there's another result by Cohn that shows that, if you have a cross product algebra, and one of the elements of the symmetry group is the modular Hamiltonian, then you go from type 3 to type 2. So you're resolving already UV singularity. So there's already a mathematical theorem that the presence of edge modes, which kind of makes sense, once you allow somehow the boundary to have certain quantum fluctuation, you can mathematically prove that you don't go to type 1, which would be like, full resolution of the singularity, but you go to type 2, which means that you have a density matrix. And the main reason it's possible here is because in gravity, the modular Hamiltonian, so what is the modular Hamiltonian? The modular Hamiltonian is the log of, it's proportional to the log of your, density matrix, or would-be density matrix, and this object here is exactly equal to the area operator. And the reason it's exactly equal to the area operator is because of the quantum constraints. Okay, so what I call this property here the quantum equivalence principle. It's not true for general field theory, but it's true for a theory of gravity that the modular Hamiltonian is kind of a geometrical object. How much time do you have?
5 minutes.
We started, yeah, you. Okay. So that was a little bit fast, but it shows you this connection between. So now I go back to this idea. This group of symmetry is really the group of symmetry of a quantum fluid. So this sphere now, suppose I live on this sphere, I can think of it as a moment operator, of a density operator. I have exactly all the elements to define a quantum fluid. In fact, the representation theory was defined. So I can think of a quantum fluid, and then the beauty is that I can say, well, and what is the analogy? The analogy is the area density is really the fluid density, the outer curvature is really the fluid vorticity. And then these are the two Casimirs, so therefore the quantum representations are labeled by what choice I make for these densities on the sphere. And we can do that semi-classically. So what is a classical fluid? The classical fluid is a fluid where both these densities are continuous with respect to the Lebesgue measure. Okay? If you take both rho and omega to be continuous with respect to the Lebesgue measure, you're describing a classical perfect fluid. But now, it's a measure, so if you think that these measures are discrete measures, these are different quantum representations of your symmetry group, then you get a quantum fluid. And in particular, this is how Landau somehow discovered the atom. He said you can discover the atom just by quantizing the symmetry group of a perfect fluid. And you can discover the nature of helium-4 by quantizing the velocity, which means you're quantizing the vorticity. So it's kind of interesting that it's kind of an effective method, but now in this effective description, I already have quantile geometry, just purely from representation theory. So this is what I'm doing here. So what's interesting is that, if you push a little bit this picture, you get some kind of constituent picture where atomization of the fluid, which is really is essentially the area constituent, and the vortex quantization is the momenta. And you can write explicitly the quantum representation labels for what these objects are, on the 2D sphere. For the density, it's kind of obvious. For the momenta, it's a little bit less obvious. They are classified by, in fact, a conformal weight and a spin, which are exactly the same labels of conformal representation you would have on the 2D sphere. And that explains the link with celestial holography. At infinity, you have the same thing, except that these excitations now, they're simply the graviton, right? And the spin here has to be true for gravity. So in finite, you get a notion of area constituent, and we're still in the continuum. I'm not putting any discretization. I'm just looking at quantum representations that now have an external number of excitations there. And so in that sense, I would say that discretization is not postulated, but kind of derived from quantum mechanics. And so now the link with loop gravity, and it was done by Wolfgang Wieland in 19, is that in ancient quantum gravity with an image parameter, you can argue that this operator here needs to be gapped. Therefore, if it needs to be gapped, somehow the discretization or the atomization is kind of a necessity. Okay, but it's really about representation theory. Now, as I say, another option that we're exploring is that area-preserving diffeomorphism is at the core of it, and we know that the area-preserving diffeomorphism can be regulated as the group of symmetry of matrix model. Okay, so let me, maybe I don't have much time here. Here was very much the static, and looking at the representation theory of this, symmetry group. What's happening right now, there's a lot of a new understanding, first at infinity, but now in finite surface, about the ratio de equation and the quantum ratio de equation. There was a talk on the other session about quantum ratio de equation, the time-like one, but here we're looking at the null one. And remarkably, now we have enough control that we know how to quantize at least at the operator level, and we're looking at the states, every kind of this simple constituent along the null rays. And there's a beautiful geometrical setting that, like at time like infinity, you can just write these conservation equations as a Carolian conservation equation. Carol means that C equal to 0 limit. Okay. And we know the canonical structure. Yeah, there's a beautiful, I mean, that slides deserve a talk, but just to give you, we understand the canonical variable, we understand the conservations equation. It took us a long time to go at, on the time-like surface, it's well known that you have a relativistic fluid. Here we understand now the nature of the Carolean fluid. So I want to take a summary. So what I presented here is that there's profound consequences of Noether theorem for gravitational theory, which leads to kind of a new picture of quantum geometry as a representation state of the corner symmetry group at every cut of entanglement here. Now, this corner symmetry group encodes non-commutativity of the geometrical observable associated with subregions. And to me, that's, they represent quantum geometry in that sense. Now, if you push it and you take seriously this representation, it leads to a discretization of space from the representation of this continuum infinite dimensional group. A little bit like, you contrast Virasoro and you find a gap and you find some discrete spectra, but this is a quantum property of representation. It's not something classical. And now, as we, there's a notion of edge mode that needs to be put there. You need to have variables that really dress your observable to tell you where you are. And these edge modes are now kind of mathematically proven to be exactly the fundamental reason at the semi-classical level between the type 3, type 2 improvement that happens in QFT. And and dynamics along null surfaces are kind of interesting. There's a wide history of horizons and quasi-horizons and gravity wave generation, but I think now we can start to look at it with a bit more of a quantum eye. Thank you.
Thank you for the beautiful talk. Are there any questions?
If I understood correctly, this is just pure gravity you are talking about.
Yeah, the group of symmetry doesn't change with matter.
Yeah, that's what I was asking.
Yeah,
if you add matter, what happens?
You have the same group. Well, but yeah, you have the same group.
The degrees of freedom, do you see them or what? I mean,
what you see is the energy and the momenta.
But then what happens? You see what do you see?
You see energy and momenta. The mechanism I described of the Noether theorem, the fact that the charges becomes a pure boundary term, it's true for any coupling to any matter. And now, if you have matter field, you can look at the reaction of how the edge modes kind of responds to the influx of matter. But in the end of the day, the matter creates a source for the gravity field in the same way that the graviton creates a source for itself. So
you don't expect any big differences.
I mean, there's going to be a big difference from the fact that now geometry is quantized. So the big difference is that the quantization of geometry has a big effect on the UV property of matter. Yeah.
But you say geometry is quantized, you mean the areas?
I mean the representations of the symmetry group. Here it's not. It's.
So that includes areas or.
One of the elements is the area, but there's much more.
Do you have like distances?
Well, the momenta contains more information. There are more charges there. There's an infinite number of charges per point. So the dictionary is I mean, for instance, people have spent, the entire literature, I mean, there's a huge part of literature on ADS-CFT in connection with quantum information, which is just about understanding the spectra of the modular operator along one null rays. And so looking at the property of that operator on one point of the sphere and looking at the rays. So you have a lot of geometrical information there that needs to be decoded.
Can you say something about the matter, like quantization matter, or is just something you put by hand?
In that picture, matter is just a source.
Yeah, thanks Laurent for the very nice summary talk, and also for connecting it with the recent discussion on the cross product. Can you actually maybe go back to the slide? So I think I didn't quite catch how the cross product is formed here? You're saying that it's built from basically the modular Hamiltonian and then essentially the dressed observables.
So there's two elements to that. First is in 2016 with William, we constructed the set of gauge invariant observable associated with the region using somehow this edge mode, which is the position of the boundary, and then we show that you have to dress an observable with respect to that position. Now, I just recently discovered that this construction that we call it the extended algebra, but then if you look at the papers of Tomita, in the 1970s, this is really, and you allow yourself to have a bigger group than usual, this is what we did with William is exactly a cross product. So the algebra of gauge invariant observable associated with region is really the naive algebra, extended with the group algebra, like a fusion. It's a cross product. It's a semi-direct product. Okay, so this will be explained in the paper to come with Elliot here. And now the link with the modular group is that you have to say, okay, so far so good. What you have to argue is that the modular group is a subgroup of the corner symmetry group. Right, so you have to kind of promote at the quantum level this equality, which is a classical equality at the quantum level. So you have to identify the area as the generator of the modular group. You could say it's either a conjecture or it's a postulate of quantum gravity. I call it the quantum equivalence principle. So I'm going to, look at this, let's say more as a postulate about quantum gravity, where you postulate that in gravity, this is what I was saying about symmetry equal entanglement. That's kind of the mathematical formulation of it.
And then maybe one last thing, since you now have a type 2 algebra, I guess you have a maximal entropy state also. Do you have a particular interpretation of that? Because in the work by Witten and so on, I guess that's related to the de Sitter.
Yeah, we're looking into that. Maximal, once you have a symmetry charge state and you have equality of the charge, there was a talk yesterday about symmetry charge. So in some sense, it's kind of very natural to say that the maximal entanglement state is the one which just share the same charge pair on both ways. But I think the type 2 is even before you re-quantize geometry, which is it's almost kind of kinematical at that level. It's kind of it's almost too easy in some sense, the Witten reduction. It's just due to the presence of the fact that the mechanism, if you think about it, is very simple. It's just that now you have an edge mode variable, and that edge mode variable has finite fluctuations, and therefore the corresponding conjugate variable, which is the modular Hamiltonian, cannot have infinite fluctuation. And if it doesn't have infinite fluctuations, you have resolved your singularities. That's kind of the mechanism behind the physical mechanism behind the technical type 3 to type 2.
Thanks. I propose we save further questions for the discussion session later, and let's thank the speaker again. Okay, and our second speaker is Manus Visser, who's going to talk about partition function for a volume of space.
All right, thank you very much for inviting me. So I will talk about work that's based, work in collaboration with Ted Jacobson, and I think it ties nicely with the presentation by Laurent, because I will also talk about finite regions and their associated gravitational entropy, but I will actually derive it using different methods, namely using the gravitational path integral. So the motivation comes really from the Bekenstein-Hawking entropy, which I think gives us a key insight into quantum gravity from low energies. So the Bekenstein-Hawking entropy is proportional to the area of the boundary, and it is indeed a quantum gravitational effect because both h bar and g appear in the formula. Now, it was originally, of course, discovered for black holes and later for cosmological horizons, but it is actually a very universal formula because it also applies to acceleration horizons, and arguably, as Laurent also mentioned, it applies actually to the area of any boundary separating a region of space. So it applies to any finite region of space, basically. So the entropy of this finite volume should be, the expectation is that it is actually given by the area of its boundary. But the question is really, how do we justify this conjecture? So I will use the methods of Gibbons and Hawking from 1977. So they derived the entropy of black holes using a saddle point approximation of the Euclidean path integral, gravitational path integral. And what we want to do is we want to write down a similar gravitational path integral or partition function for finite volumes of space, and then take a saddle point approximation and then derive the entropy. And we will do this by using the method of so-called constrained instantons or constrained gravitational path integrals. So the difference with their work is that we have to impose some constraint to fix the size of this region. Okay, so let me briefly review what Gibbons and Hawking did. So they represented the thermal canonical partition function in gravity by a gravitational path integral over Euclidean metrics, where I is the Euclidean action, say for GR. And then they take a saddle point approximation, and in that case, if the on-shell action is much larger than h bar, then you can approximate the partition function in this way, as we have heard many times. Now they applied it to black holes, but also, in fact, in their original paper already to Euclidean de Sitter space. So Euclidean de Sitter space is a round sphere whose radius is set by the cosmological constant, or by the de Sitter curvature scale L. So it has topology as D, but it's actually a round sphere. And if you evaluate the action of general relativity plus cosmological constant, positive cosmological constant, if you evaluate that on this saddle, then you get minus the area over 4G, so minus the de Sitter entropy. Now, what does this computation mean? It means actually that the partition function is in this zero loop saddle point approximation is equal to e to the s. And how should we interpret this? Well, since de Sitter is a compact space, Euclidean de Sitter is a compact space, the energy is actually zero, because energy in gravity is always defined on a boundary. So the energy is zero, but this means that, so energy is zero, but this means that the partition function is just trace of 1. So it's trace of 1, so this is actually over the entire Hilbert space, so it just computes the dimension of the entire Hilbert space. So one way to think about this answer e to the s is that it is equal to the dimension of the Hilbert space of states surrounded by this cosmological horizon. Okay, so that was the Gibbons-Hawking computation. So now we want to generalize it to finite volumes of space. And as I already mentioned, in order to talk about a finite region, we have to somehow fix its size. And one thing we thought about is fixing the area, but that didn't work. And so what we did is we fixed the spatial volume of our spatial region. And so we impose an extra constraint in the path integral that fixes this volume V. Now you can represent this delta function in a different way using a Lagrange multiplier. So then you get an integral over the Lagrange multiplier and then an extra exponential. So e to the lambda and then c minus v. So c is the constraint. Okay, so now we will just do this where the Euclidean action is given by general relativity. And yeah, so lambda is imaginary, so it's along the imaginary axis. That's correct. Okay, so before I do this computation, let me first mention what the metrics are that we integrate over. So what are the topologies that we integrate over? So what we do is we consider a topological d-1 ball. So big D is the number of space-time dimensions. So a codimension 1 topological ball whose boundary has the topology of a sphere. And since we work in Euclidean signature, we want to rotate this ball around the Euclidean time circle, but the boundary should be a fixed point. And if you do that, you get the topology of a D-sphere, just like in de Sitter space. And one way to visualize this is in 2 dimensions, so 1 + 1 space-time dimensions. So then the ball is just a line, and the boundary, the S0, is 2 points. So if you rotate this line along the Euclidean circle by fixing these 2 points, you get a 2-sphere. And this generalizes to higher dimensions, so then you get a D-sphere. Okay, so now this is our partition function represented as a constrained path integral, where we have this lambda, and we will look at the situation where the action, there's some low energy effective field theory, where the action is given by GR, and we also allow for a cosmological constant. And what we do is we foliate this ball, we foliate the sphere by d-1 balls, as I already mentioned, and they are at constant phi. And we impose the condition that for all constant phi slices, the volume is the same. The spatial volume is the same. So this gamma here is the induced metric on this slice, and n you can think about as the lapse. So now what we have to do, what we do is we take a saddle point approximation, and in that case you get the Einstein equation from this part, but you get it. It's actually sourced by an effective perfect fluid because of this term, and the perfect fluid has vanishing energy density, but it has a pressure. So the saddle point equations take this form, where the stress tensor is that of a perfect fluid with pressure given by lambda over n. All right, so now we will look for solutions of this saddle point equations, and we will just look for the simplest solutions that you can think of: static, spherically symmetric solutions. And these are the solutions. So for lambda is 0. We also have solutions for a positive and negative cosmological constant, but this is like the simplest solution you can think of. So the spatial metric is completely just flat, just Euclidean space. And this is the time component, Euclidean time component. And notice that it has a horizon that R is RV, where RV is set by the volume, big V. And this saddle has topology as D. It is conformally flat, in fact, but it has a curvature singularity at the horizon, at R is RV. Now, even though it has a curvature singularity, you can compute the Euclidean action. You can take it on shell, and it's actually finite. And if you do that computation for a 0 cosmological constant, but this generalizes as well, you get minus A over 4G. So you get precisely the Bekenstein-Hawking entropy in this saddle approximation in the 0 loop approximation. And so this generalizes the Gibbons-Hawking partition function to a finite volume of space. All right, and as I said, there's an interesting generalization to other, to positive or negative cosmological constant, but you get the same result. Right, and in a specific case, actually, where the volume is equal to the de Sitter static patch, you obtain the result of Gibbons and Hawking. So in that sense, it's really a generalization. Now, to conclude, we talked about we constructed the partition function for a volume of space, and we argued that it is actually the dimension of the quantum gravity Hilbert space of a topological ball of fixed volume, fixed spatial volume. And in the saddle approximation, this Hilbert space dimension matches with the Bekenstein-Hawking entropy attributed to spatial regions. So we get e to the a over 4g. And for future directions, we would like to understand this curvature singularity better, and perhaps see whether higher curvature corrections regularize this singularity at the horizon. Thank you.
Thank you. Any questions?
Thank you for the nice talk. I'm just wondering, compared to the standard approach where you just periodically identify the Euclidean time
Right.
to get rid of the conical singularity.
Right, we
at the
also do
horizon,
that.
You have done this already, and now
Yeah.
you just have a different curvature singularity
Yeah.
that you still need to deal
Exactly. So the conical singularity is removed, but then you still have a curvature, another curvature singularity.
with. So in the usual approach, I think you know, in the saddle point approximation, it's like an effective field theory thing. You have Einstein-Hilbert, and so you don't want to include singular geometries because presumably if the curvature is very high, you would need higher curvature corrections already in the action to account for those. But now you have a singularity, so is that consistent with your use of Einstein-Hilbert without any correction?
Yeah, that's a very good question. So it would only be consistent if the higher curvature corrections somehow smoothen out.
Okay, so they have to cancel out
Yeah.
somehow from. Okay.
Yeah. And we still have to investigate that.
Right, thanks.
Yeah, thanks for the talk. Just a quick, maybe naive question. So it struck me that you look at fixed proper volume again, and in this first derivation of the Einstein equations from entanglement equilibrium by Ted,
Right.
we also used entropy variation at fixed volume, and in that derivation, although it's a bit question why one would have to fix the volume. Does your approach here shed any new light on it? Because I guess you can use that
Yeah, exactly.
partition function to vary it and then plug it basically into his old proposal, right?
Exactly, yeah. So we believe that this could give a proof of that conjecture by Ted.
Okay.
Precisely because in fact, of course, this work was motivated by Ted's original work. I didn't mention that, but precisely because he fixes the spatial volume, and we get the entropy. We get the entropy for this fixed spatial volume partition function, and actually it's the entropy of a maximally mixed state. So adding matter, for instance, should lower the entropy, and that's precisely his conjecture, namely that the entropy of the vacuum is maximal at fixed spatial volume, and that if you add matter then or curvature, then it lowers the entropy.
Okay, yeah, very nice. Look forward
And-
to more. Sorry.
Yeah. So no, we have to investigate that more as well. And one of the open questions in that conjecture was whether the entropy of the vacuum is maximal or minimal. So you can prove from GR, if you look at first order variations, that the entropy is stationary in the vacuum, but it doesn't tell you whether it is maximal or minimal. And so this suggests that it is maximal, but we would like to understand it better.
Yeah, very nice. I look forward to hearing more about that.
Okay, so let's thank the speaker again. By Goffredo Kirko, who's going to talk about multipartite entanglement of random spin networks in quantum gravity.
Okay, thank you, Thomas. I'd like to thank first the organizers for the possibility to talk. I mean, so far it's been a really beautiful conference. So today we start hearing about the importance, the impact of entanglement in quantum gravity, and what I'm going to present to you today is like a simple exercise from the quantum gravity point of view. In fact, it's something more related to quantum space, so it's toward quantum gravity, which on the other hand involves some complicated techniques from quantum information theory, which then would be simple from a conceptual point of view, but maybe technical. So let me show. So the point is, okay, it was amazing to have Jan de Boer today and Hal really introducing this context for me. And yeah, entanglement has been, I mean, a very key conceptual feature in quantum gravity in the last decades, maybe more than 10 years now. And I mean, from the first step, passing from the Becker-Steenhoeken entropy-area-entropy relation to, can you hear me? Right. To the Ryuta-Kanagi formula, okay, for in IDSFT, then, you know, suggesting in this sense the possibility to reconstruct space and space-time, in fact, from the entanglement structure of the boundary, in that case in IDSFT, down to local holography, which Laurent already discussed in a new context now, from the original work of Mia and Takayanagi, to the new, I mean, information that we are gaining from a lot of techniques implied from quantum information theory implied in what is the quantum black hole paradigm and information paradox, but you know, like replica wormholes techniques and so on. And down to the very radical idea then, eventually quantum, I mean, space and time can be emergent from entanglement, okay? And so why the title of my talk? So most of these deduction conceptually came from the use of entanglement entropy. So from essential bipartitioning of Hilbert spaces, and we see that already now. I mean, exactly this bipartitioning is what is you know, focusing our attention on the issue of separability, finding algebra subsystems, and the way we glue, okay, subsystems or a portion of space-time in particular in quantum gravity. But I mean, going beyond these results also means to, you know, investigate more from a quantum information point of view, like structure, like multipartite entanglement or different measures. So in this sense, and in particular, going to non-perturbative and Becker-independent contexts, like a loop quantum gravity, as we saw this morning, is a pretty precious tool. I mean, to test somehow these ideas in a very quantitative way. Okay, so in loop quantum gravity, we have. I mean, we know that we don't have a full theory. We know we have issues with dynamics, but we also know that we have a very reliable description of quantum space, at least, and we have a clear Hilbert space description. Okay, so in particular, okay, as we saw today, in loop quantum gravity, we have a kinematic Hilbert space, okay, which is an L2 space of function defined on holonomies of the SU2 Ashtekar-Barbero connection, okay, where we, at least at the first step, we can impose SU2 gauge symmetry. So we have SU2 gauge symmetric functional, and so we have this particular structure, the space, which is sum over irreducible representations of SU2 of something which factorize. Okay, yeah. So on this Hilbert space, we know. I mean, nowadays also, so we have what we already discussed. So the fact that we cannot factorize a space, but we can at least look at each superselection level and see, I mean, how quantities can be defined. And this is what we are going to do effectively. So we are going to measure entanglement at the level of each sector, okay? So, so in order to somehow leverage or acquire techniques from quantum information theory, in the last few years we slightly changed our description of spin networks, in a sense. Also, we tend to see spin networks, so purely derived from quantum gravity, for instance, as tensor networks, as peculiar SU2 gauge invariant tensor networks. And in fact, this is a way to see them that which allows to directly transfer our know-how in condensed matter to our states here. So our states here are basically contractions of some physical state which lives, so is supposed to live on the nodes of a spin network in terms of project some edges which basically glue nodes among each other. These edges, in our case, are related to some physical some physical description, which is so they are not purely they're not just gluing nodes among each other like in a standard tensor network. So they're not purely virtual objects, but they are related to Wilson lines. So they carry, information about holonomies. So we have to take this into account, because this in particular brings information about topological non-trivial connectivity, for example, of the graph into play, something which is never discussed at the level of, for example, of random tensor networks results. Okay, so in this case, so we have our basic state is something which has a core which lives on these nodes, which can be arbitrarily generically entangled. Okay, and then there is a connectivity which is induced by the support of the graph on which our functional finds support. Okay, so this is a standard spin network, but what we know it is are interested in are in fact boundaries, and it's more and more interesting to look at corners effectively of what were discussed so far, even if in a much rude way here. So to spin networks basically which are cut out of something of actual gauge invariant wave functional. Okay, so imagine you have your wave function which is a gauge invariant object here. So everything is contracted and gauge invariance is imposed locally, but then achieved at the global scale, and then you cut out the region. Okay. Now suddenly you have these degrees of freedom here coming out, which in this case are just like spin magnetic indices, but they would be like dressed properly in a context like the one Laurent discussed, which define a boundary. Okay, define a boundary. And when you have a boundary, in fact, your functional is not anymore valued in C. It's something which lives in an Hilbert space, which is the boundary Hilbert space. So the very spin network itself, by itself defines a bulk-to-boundary map. Okay. And the properties of this bulk-to-boundary map, like the holographic properties, this is something which really recalls like a quantum error correcting code once you put a bulk on it. No? And so the properties of entanglement, of maximal entanglement of these edges, are related to properties of isometry of this map, and you can study these properties as we did, for example, or Eugenia Colafranceschi did recently, and Simon also discussed about these points. Okay, but so this is our starting point in a sense, and what we want to add to this basic structure, which is really in one-to-one, can be mapped in one-to-one to a standard tensor network object in condensed matter, is the fact that we have non-trivial holonomies. Okay, so this object really carries non-trivial holonomies, and in fact, if you have non-trivial holonomies, this means that this structure actually carry curvature. Okay. So at the end of the day, so we want to see how much information from the bulk we can recover from the quantum correlations that we have on the projected state on the boundary. So this is the point. So how do we do that? So we have to squeeze somehow all the information about the curvature into degrees of freedom which are very simplified and can be described in terms of in simple terms. So we act by standard techniques in loop quantum gravity. So we use like a reduction by gauge fixing. We exploit gauge fixing at each node in order to squeeze locally, if you want, in a given region of a certain radius of your network, all the non-trivial information about the holonomy on vertices. And we imagine we can do that distributedly, uniformly through the network in order to have something like that, so something where your non-trivial holonomy, so curvature somehow, is attached to each node. This is not enough, of course. This is already somehow too complicated. We want to partially coarse-grain to encode the information about the holonomy and non-trivial holonomy in something more simple, which is just what we call a tag. This was, standard literature from Etera, Levine, and actually Laurent itself. So we have this holonomy. We imagine to coarse-grain this graph by unfolding the intertwiners. So these intertwiners are just a recoupling of spin representation associated to these Wilson lines. Imagine. So you can always think of unfold the Hilbert space of your node, and once you did that, you can trace over it. So you can coarse-grain, in a sense, the information about the holonomy, and you end up with a spin now, which is reminiscent of what you were carrying out. So there is a closure defect spin, so a spin which measures the amount of flux that you are, eliminated by integrating over the holonomy. And this is a closure defect, has to do with clearly with curvature, as today I'll explain to us intrinsic curvature piling up at the node. Okay, so once you have this object, basically you can see these spins as basically measuring the non-closureness at the nodes, which now become not anymore gauge invariant. And in this sense, you can think of this hedge spin inside. So you have some spins at the boundary, so boundary degrees of freedom, but you have some spins in the bulk, which are still boundary degrees of freedom in a sense, because they are associated to some open region, okay, in the bulk. And in this sense, this allows you, in this very simplified model, to define an Hilbert space, which is, again, a direct sum of something which factorize of a boundary, which is an external boundary and an internal boundary. And since this internal boundary reflects the curvature of the associated to the non-trivial holonomies of the graph, then, of course, what we're going to do, we're going to measure the correlations between internal curvature and external boundary. Okay? So your state now will be a bulk-to-boundary state, which though lives in an extended boundary, and you can see that correlations about the actual boundary and the inner boundary carry all the information about the bulk. Okay? So how do you recover this information from, for instance, a purely boundary observer? So the take we take this point of view. So we consider a boundary observer we make a random measurement in order to simplify the state again. So we partially trivialize the bulk, okay, in a sense by using projecting vertices with random vertex states, and we end up with a density matrix, okay, which is just a contraction, the bulk contraction of bulk and edges as before, plus this projector, okay. Now we work, as I was saying at the beginning, with fixed J's, so it's again a very simplified setting in the context of loop, so we lose basically a lot of degrees of freedom, and we look at a tree partition now. A tree partition is related now to bulk, tag spins, Hilbert space, and boundary spins, which are now divided into two parts. Okay, so imagine you have you are an observer at the boundary. You don't see the tags from the bulk, so you don't see the curvature. You just see the boundary, and you pretend to do like a bipartition of the boundary. So you have an environment which will affect, okay, the correlations of your boundary. And this is a typical setting of a tripartite analysis, which is, by the way, also the one that is used as a starting point for the replica wormhole in IDSCFT. So actually, those are very, very similar techniques. So which measure of multipartite entanglement in this case we use? We use a measure which is called negativity. That's why, how many minutes? A few minutes? 1 minute? 0 minutes, okay. This is a measure which is well suited for mixed states, because now we have an environment, so our boundary is not anymore a pure state. We need to use this quantum negativity. This is a faithful measure, though it's not a measure which is a quantitative. You cannot actually tell how much entanglement there is. I mean, you can say whether a state is not separable if negativity is non-zero. Okay, so is a witness of entanglement in a sense. Okay, so let me go very quick. So we, of course, as you have seen many times in this setting, you never go for actual calculation of quantum entanglement or entanglement entropy, and even in this case entanglement negativity, you go for Reni. Generalization of it, and then you take the analytic continuation to k equals 1. Okay, this allows to simplify the calculation in a sense, and also the fact of starting from a random tensor network here plays a fundamental role, because in a typical regime, basically we know that the expected value of our quantity will match the actual value. We can prove this point, but also, I mean, we know that we can approximate this Rene negativity in terms of basically a ratio of partition function, okay, which are given by the trace of the momenta. So the momenta of this partially transposed density matrix. Okay, let me skip the details, but let me at least show you the details, the details of the results. Okay, so at the end of the day, like this complicated calculation, which basically is a diagrammatic way to compute these partition functions, which will be the partition function of a generalized Ising model, where basically on the very spin network, I mean, the randomness allows you to map the quantum system to a classical system where spins are replaced by a permutation operator. We end up with an action. This action has a topological and an intertwiner related that we call physical contribution, okay, and the negativity. So the topological part is the one that we focus on here, And just to show you that the negativity for a very simple graph like that can be computed and gives you a very rich entanglement phase diagram, if you want. So we have three. So depending basically on the dimension of the three subsystems, so boundary A, boundary A1, boundary A2, and bulk environment, you have three configurations. So one is a whole configuration where basically the environment is so big that basically you have a disconnection, or if you want a complete thermalization of the boundary. The second point is a bipartite regime, so where the environment is so small that basically you are back to a bipartite setting. And then the last one, which is the most interesting one, which is an island.
Sorry to interrupt you, but can we go to the conclusion?
Yes. So this conclusion is that here is the conclusion. So in particular, in a specific regime, which is the island regime, you see that the negativity is proportional to the area, okay, minus linear correction depending on the TAC contribution. And so since our initial general goal was to basically measure geometric quantities in terms of quantum information or quantum information inspired quantities, then this is very interesting, because at the end, I mean, you realize that what is telling you this result is not just something related to the area, but is something related to the curvature. So since we start from injecting curvature in our problem, then we see that we are able to recover curvature from this analysis. So, okay, basically this is a summary. So we tried these techniques, and we saw that these techniques apply to our setting. We are measure like quantum negativity, so reflect the topology, the connectivity of the graph. We find area scaling behaviors like Ryuta Kainagi in our system, but also like we have a bulk term, which is basically the analog of quantum corrections in the Ryuta Kainagi in a DSFT, and essentially, yeah, with a multipartite, so with a tripartite setting, so going beyond entanglement entropy, we are able to add an extra ingredient to our geometry entanglement correspondence, which is somehow curvature. So curvature can be expressed as in terms of relation of what I didn't show you, mutual information and bipartite entanglement entropy. Okay, and yeah, now there are more speculative things which may be discussed maybe later if you have some questions. So thank you. Sorry for being so squeeze.
Okay, thank you. Due to lack of time, I propose we immediately go to the discussion session where we can ask questions to every speaker. So if there are questions to any speaker, please.
This is a sort of question/comment for Laurent in his talk. So this dressing to the boundary, or basically to the corner, implicitly assumes that there are degrees of freedom that correspond to these edge modes in the theory. And it's not really clear that those should fundamentally be part of the theory. That's part of the reason why in thinking about dressing in some of the earlier work, we looked at dressing off to infinity, for example. And of course, when you consider all the diffeomorphisms, you're sort of ignoring the diffeomorphisms that move the boundary. So could you say a few more words about how we should think about these basically edge modes, and whether, in some sense they're just ad hoc degrees of freedom that you introduce, and whether you think they have some more fundamental significance?
Yeah, thanks for the question. Yes, I agree that. Yeah, first, so the thing which is really established is that you have this kind of a symmetry group here, which is there at the corner, and then that the action of your symmetry group on the states. So you need, it's clear that you need to add some dressing in order to represent this group. So essentially, these dressings they're there as states of representation of this group.
But it's not just dressing, but you have to fix a region, and then you're breaking the diff symmetry.
Exactly, you have to fix the region, you have to break the symmetry, and now I want to say, well, if I want to talk about a state inside, I have to pick a representation, let's say, of that symmetry group. Effectively, when I do that, I kind of I now have states of different which have the same, which are transformed into discharge. So what you're asking is, in the way I was presenting, I'm saying, okay, I'm just adding them there to fix the location. So now, and in fact, it relates to what you're doing or what Philippe is doing too. So now there's the questions of, well, how can I think of these dressing modes as some kind of physical mode? So either, attached to some fixed boundary, like Philippe is doing, or attached to kind of infinity, or maybe to I naught, if really I don't care about my region. In my case, recently, because I'm thinking of an interferometry experiment, inspired by Catherine picture, I'm thinking maybe I want to kind of attach them to the diamond itself in some sense, right? So make them a bit more local, and then ultimately, I want to think of them as something physical in the sense. And one evidence for that, and it's not an evidence, but it's kind of a hope, is this type 2 to type 3, which is something very simple. It's just that if you add one dressing, if you just add one mode, which is the one conjugated to the modular Hamiltonian, there's many more modes that you need to kind of fix. But if you have this one mode, somehow you have a mechanism to resolve UV singularity, just based on the fact that it's about putting part of the phase space, the fact that this location of that sphere cannot be exactly well defined. And then, I think it's an interesting question of finding the physical mechanism in which to which they respond, right? Whether you attach them at infinity, whether it attached to the center of the interferometer, or whether you can even think as some kind of fundamental extra object. Does that answer?
I think so. Yeah, I think that, well, in some sense, the dressing is physical, but the question is whether you're dressing it to something physical, and maybe that's part of the.
Yeah, exactly. Right now, I was describing as some kind of quasi-local mode, and then the question is that if I have two different corners and they talk to each other, then you need to have some kind of relationship. Yeah, I agree. But we will agree that it's physical. Now, with respect to what, with respect to the setting, I think that's the discussion.
Let me maybe just quickly follow up on that, since you already mentioned this. So in our works, we actually took more a global perspective on these subregions in the sense of being embedded in the global space-time, and then you can indeed, for instance, also along the lines of your works of dressings, define the edge mode fields actually as coming from Wilson lines that are attached to some asymptotic structure or something like this. But then from the global theory, you can actually do some kind of post-selection procedure where you reduce to a subregion theory. And so from the global point of view, these edge mode fields are not new degrees of freedom. They're just built out of the field content that's already there. But when you do this post-selection to a subregion, they actually appear as new degrees of freedom for the subregion phase space. And why are they new? Because they have support, for instance, in the causal complement of the subregion, and so you can vary them independently. And so that actually also explains why the symmetries that you get on the corner, why they, for example, also are consistent with symmetries of the global theory. So they just correspond to when you do such symmetry transformations, it basically corresponds to changing initial data in the causal complement. So and then if you do it this way, you actually recover all the things that Laurent and so on did in their original works.
Any further question? Do you mind?
Okay. Anyway, so the question is, I like the point of view of starting with, I'm going to see an exercise to do local physics and have a part of the space-time and the other, the exterior. But then from that point of view, eventually I have to probably try to cover more of space-time, like if I have a Cauchy surface divided into with some charts, and I study the causal diamond of each chart. Then you have two that intersect, and then they should like complement each other. But at the beginning, you said that you were going to have the same algebra and the same everything for things that they have the same topology. You know, so if you have two balls, they intersect. So can you comment on that?
Yeah, it's interesting you mentioned topology. So it's true that if you have a sphere topology, the algebra is universal. Of course, if you have torus, I never mentioned that, we never use that, but you have central charges, for instance, that appear.
But
if you have GSG, you would have...
If you have two balls, they intersect and they join into another ball.
And I think your analogy, so what I'm saying is that somehow the symmetrical pyrother code is the same. The modes that these guys transform are these edge modes. Of course, what happens is you want to do a quantum gluing of states, which, I view a little bit like when you have two open sets and then you find the overlap between them, you glue them. And then what happens at the quantum level, so it's like almost like a quantum coordinate charts. What happens there is that, as Philippe was saying, you have to take the maximally entangled states, of course, which, the entanglement is carried by this edge mode and it kind of disappears. In the same way that if you have two open sets, you glue. Now it's kind of an analogy, and it would be interesting to see whether there's a quantum Riemannian picture. Is that where you're going about it? But the universalities maybe that I was talking about is the universality of the type of charts I have to use to glue the two subregions, because it's kind of a local property.
My question is, what happens if you have a black hole inside? If your sphere is a horizon?
Yeah. So if the sphere is an horizon, a lot of things simplifies, because then that surface. So the case where the relationship between modular geometry and symmetry was clear was before this kind of general case, was always in the case where you have a Killing vector field, right? So you have a symmetry. So if you have a symmetry and your horizon, your entangling surface is preserved by that symmetry, then you don't need gravity for the modular Hamiltonian to be geometric. In general, the modular Hamiltonian is a completely non-local object that you have no control about. And so that's why people just focused on horizon before, because it's only this particular, and there you don't need gravity. Okay? But gravity, allow you to free yourself from just restricting to horizons. So in horizons, it's much simpler for sure.
You mean, but does it help you with any questions about black holes? My understanding
well,
is that you would seems to be everything is regular. You don't have any problems.
My perspective there is that the intuition that came from the black hole is kind of universal, maybe along the line of Bianchi, Myers, and more recent works. In some sense, we all felt that there's something universal about this. Why do we care about black hole? It's just one solution. Otherwise, if it's not something universal, it's just one solution among GR for one particular surface.
Black holes are not special at all, In your picture,
no, they are special. They are special. They are very special because they are.
Can you see something? Can you infer something from your analysis about the black holes, or for you it doesn't matter? Is it a black hole or just empty space?
Well, I think a lot of people have inferred most of what they can do on canonical horizon, the thermality of it, and the geometrical entropy. All of that has been, done and done.
No, but I'm asking, in your approach, do you get something new? Do you see something new?
Well, what I get new is that I want to say that this correspondence between geometry and entanglement, if you want, and statistics and geometry is quasi-local. It's not just global.
So maybe one more question, preferably to one of the other.
Hey. My question is for Goffredo. So I know you didn't have time to go through all the stuff.
Sorry about it.
I just wanted to know, like, how did you recover the curvature notion in this tripartite entanglement picture?
Yeah.
Like the idea, like, did you do some coarse graining? How do you recover it? Yeah.
So the idea is that basically, so you had squeezed in your description. You have a tripartite system, and one of these parts is somehow related to curvature. Okay, and then you ask, can I recover this information from the entanglement of the rest? Okay, and the answer was yes. I mean, this is an entanglement measure via this quantum negativity, which is a new measure in a sense. And is it sensitive to that? And the answer was yes, it is. And it was very nice how it came out. I mean, because basically in this particular regime that so the three regimes that I showed are nicely related to the properties of separability, or if you want, along the line of, I mean, what of the idea that no entanglement means no connectivity of space, where space-time maybe eventually. You really see that in the three cases. You see that when your environment is very, very big, then your boundary get thermalized basically, and this looks really like what we have at the Big Bang, for instance, or at some singularity. We have a large curvature and something around it which looks thermal. Then you lose. I mean, you squeeze your environment, and I mean you pass to a regime where the three parts balance somehow, and there is where you see that the negativity, which turns out to be the mutual information, actually, is related to the bipartite entanglement minus a correction. But if you think of, since you have in loop quantum gravity a nice mapping between bipartite entanglement and area, then you can show that this mutual information as an area minus something is really like analogous to the way you define Riemannian curvature in you know, by approximation even in the discrete case. You have something like a ratio of curved area which would be mutual information with the area of a flat ball, which would be bipartite entanglement, 1 minus something which is the intrinsic curvature or Riemannian curvature times some extra scale which we don't know how to. So I mean, what we find, and I couldn't show you properly, is that I mean, having three parts gives you more information about I mean, the dual geometric description of your quantum correlations. Okay.
Okay, I think we should close the session. So let's thank all three of the speakers again.